Okay, so good afternoon. Let's get started. I am DK Panda from Ohio State University, and my colleague Dr. Hari Subramani. Would you like to introduce?
Hi all, my name is Hari Subramani. I'm a research scientist at the Ohio State University. Glad to virtually meet you.
Yeah, so we have an exciting tutorial for you for the afternoon. Some of you joined the tutorial which I offered with two other colleagues in the morning on the high performance deep learning, machine learning. But in this one, we'll go into much more details on the networking technologies for HPC, which aligns very much well with the overall theme of the Hot Interconnect conference. Before we go into more details, I know it is afternoon, at least in the West Coast, and here in the late afternoon in the East Coast. Might be a few of you can just introduce yourself. Just tell us a little bit about your background, why you are attending this tutorial. That will help us a lot. Any volunteers?
Hello, can you hear me?
Yes, yes.
Yeah, hi, this is Sharan Kalwani here. I take care of high performance computing here in the industry sector. And I will just say one thing, no matter how many times I attend your tutorial, I learned something new.
Thank you. Thank you.
That itself is worth it.
Yeah. Thank you. I mean, the technology has been changing. We continuously update our tutorials. Hope you will find a lot of new things today. Anybody else? Any one or two more people? Okay, so if not, let's get started. And I'm sure like you are getting warmed up, and we'll be, please feel free to ask questions as we go along. We have the chat channel. We also have the Slack channel from the conference open, so we can answer on either of these things. And give me 1 minute. So this is how the tutorial outline looks like. We have a lot of materials to cover. We'll start with a very high level introduction with a almost 100,000 feet level. Then go into some more details on Infiniband and high-speed Ethernet. This is where like 20 years back, a lot of new type of things started. We'll start with that. Then we'll go into some convergence, what is happening in the field, Infiniband, high-speed Ethernet, and convergence. Some of you might have heard of Rocky, Rdma over converged enhanced Ethernet. So we'll talk about that. So once you get an idea of some of these commodity networking, then we'll try to add on top of those. So we'll take a look at omnipath architecture. We'll take a look at NVLink, NV switch, Amazon EFA. Then we'll go into a little bit of proprietary stuffs like a Cray Slingshot, Fujitsu Tofu, which is being used in the #1 system now. Cray Slingshot is being planned for the next exascale systems. And once we get all these overviews, at least we'll take some of the commodity ones like IB, omnipath, high-speed Ethernet. Will give an overview of products and installations if you people are trying to deploy a system or trying to know more about it, how to contact, where to contact. Then we'll try to show some sample case studies and performance numbers on the very latest generation hardware, how these numbers compare with each other, how those numbers look. We have also put together, just like in the morning tutorial, we have put together some hands-on exercises. We have an Infiniband cluster here. So before the break, we'll try to even tell you like how to log on and all. And then we have some exercises there. Depending on the time, we'll try to see how to proceed and then conclude. And we have 3 hours. And the way we are planning is that we'll continue up to 1.5 hours. So that is like a 2:30 West Coast and 5:30 East Coast. We'll take a 15 minutes break, and then after that we'll continue. So that's how will be the format will look like. So if you take a look at very high level, I know HPC has been there for many years. A lot of actions are taking place, next generation application as well as computing, especially processor performance, not just the absolute performance, but the density. Chip density has been doubling every 18 months. I mean, the very latest systems, if you see the AMD, EPIC, the Rome and Milan have 128 cores per node, like a 64 cores per sockets. So that is helping us a significant growth in the processor performance. Now, of course, you can do something within a single node, even up to 128 cores. But if your application requires many more cores, then how do you do it? So this is the scale out comes in, and you need some kind of a network to connect it. And in parallel, just like the CPU technology is evolving, the networking technology is also evolving in terms of commodity networking. And these days, if you have budgets, you can actually buy commodity CPUs, GPUs, storage, networking, and put them together with some open source stacks. And this is the field of the cluster computing. And we are riding that curve, and then the clusters are becoming very popular choice for the deployment of HPC systems. Now, this is the data. Means 2 months back, some of you would have heard about like the top 500. That's the June list got announced. So there is a very interesting trend. This data has been taken from top 500. It has a lot of historical data. You can actually generate this graph yourself. In the what it's trying to show, this is the x-axis is time, y-axis is the number of clusters. Out of 500, how many of them are commodity clusters? Okay, when I say that it's a commodity clusters, that means compared to, let's say, very old days, like the craze, connection machines, if some of you would be knowing those terminologies, those used to be very proprietary system. Even Blue Gene, let's say IBM Blue Gene, you have to buy the entire system. You cannot buy in pieces or parts. Okay. But on the other hand, as I said, like if you want to buy some CPU nodes, GPUs, some network and put it together, that becomes like a commodity cluster. So now see the trend in the very almost like 27 years back, it used to be very low, but now on the latest June 21, it's 98.8% of the top 500 systems are clusters. Okay, so this is where you see how the commodity things are picking up. So that is just the trend. Now let's go into a little bit more details. I mean, whenever we talk about clusters, always people have this notion that, okay, compute cluster, like I just have in your lab or in your machine or somewhere, you have a bunch of nodes connected together to deliver the compute. But the cluster concept is not just limited to that. You can also have the cluster concept being used in the storage, because these days with all the big data, deep learning, AI, people are operating on petabytes, exabytes of data. You cannot put it into a single node. So there again, you may need to connect a lot of servers together. So broadly, if you see, physically they are the same. Like this computing node might be very similar here. You can have some memory difference, memory amount or speed, but the broad idea is that you have a set of compute servers. Here also you have a set of compute servers. You have some network. You have some network here. And the third thing is actually the multi-tier data centers. And this is where actually there's a big market out there. I'm sure I think each one of you would have purchased some things from Amazon or eBay or somewhere, okay? So if you take a look at these are called multi-tier data centers. So let's say it's Amazon. If you try to search for Amazon.com, your request will get actually linked to or get connected to one of the front-end servers. It could be in your locality, in your city, or your state. So then you start doing some search saying, I'm looking for this book. So your request gets moved to the tier 2. So these are the app servers. And this is where you will get a reply back after the search takes place. You will get a reply back saying, okay, there are so many books, so many used books, so many old books. These are the prices. It can also give you more information saying X percentage of people who purchase this book also purchase this book. So a lot of data comes out. So those are the responsibility of these app servers. And then after that, if you decide to purchase the system, then your request gets moved to the tier 3, which is the database server. So there it asks for your shipping address, your credit card, all those things. The transaction takes place. And then you get a reply back saying, this is your confirmation number. Your things will be shipped on such and such date, and your response comes back. So this is how a typical data center looks like. Okay. In the modern days, e-commerce, you will see that everybody interacts with these kind of systems every day on a daily basis. For some of you might be on an hourly basis also. Now, these are individual things, but for a multi national organizations or even some of the banks, insurance companies, you may also see that all of them are connected. So might be on a bank, the end users are interacting with the portal. The bank is trying to run its own computational model, the financial modeling, and all of them are accessing their backend storage. So this is where kind of the cluster computing is evolving, not just purely from this compute side, but also trying to take a look at over local area network, wide area network. So in this context, if you see the role of network, either here or here or here, is becoming very important. And this is where a lot of companies are coming up with innovations, innovative products, so that they are competing. And this is what we are trying to, as an end users, we are seeing the benefits of the growth of the cluster computing. And same thing is also happening in the cloud environment. Instead of on-premise, now if you go to a cloud or Azure or AWS or Oracle, very similar ideas you will see. Instead of physical machines, these are virtual machines. So you will be getting some VMs. So they may be running on the physical machine, either in an exclusive manner or in a shared manner, depending on the policies. And network file system is also virtual. Okay. So here also, there is a big significant role for the networking. And nowadays also, like especially with the deep learning and AI, there is a lot of focus on the GPUs. We are having these all high performance clusters. If you take a look at the November 28th, this is a little bit last year's thing. You have a lot of commodity clusters. There is a DJX1, DJX2. These are the dedicated systems coming from AI, from NVIDIA. You also have a lot of CPU-based systems are also coming up, including the next generation systems. So if you take a broad look at these systems, especially in this tutorial, we'll try to ask questions. What are the networking and IO requirements? Okay, because I will start with that fundamental questions. And then the answer, if you ask this, a standard answer will come with saying good system area network with excellent performance. Okay, but then the question is, how do we define the performance? In the very old days, there used to be two metrics, latency and bandwidth. So the latency is the time I want to send a data from one node to the other node. Typically, there are some tests which tries to, I send a ping pong, like I send you a message, the server, the other side replies back, and I divide it by 2. It is a one-way latency. And the bandwidth is the rate at which I push data from one end to the other end. This used to be the two metrics. But over the last 30 years, there's a lot of discussion going on, and we'll go into that much more details in the next part of the tutorial. Is called CPU utilization. And this is the CPU utilization for protocol processing. It is not just for computation, it is for communication. Okay. For example, when I want to send this data, somebody has to do some processing. Okay. I have to put together some packets, have to take it out, the packets, messages, checking for headers. So it requires some processing. So who does that and how we do that? So this is where, for example, let's say you have two technologies, A and B, and both of them have equal latency and equal bandwidth. Okay. But let's say the network A has CPU utilization of 5%, whereas the network B has CPU utilization of 30%. Which one would you like to prefer? Any answer? A or B? Again, A and B have both similar latency bandwidth, but A has a 5% CPU utilization and B is for 30%. You can post your answer in the chat or unmute yourself and tell us. A, okay. Okay, A. So two answers we got A. So of course, now the question is, okay, A, because we'll go into the details. The thing is the CPU utilization. What we'll see is that when we are trying to do communication protocol processing, A will require less CPU cycles so that more CPU cycles are left for the application. So this is supposed to give you good performance. But then you can ask the question, what is the cost? Okay, because we have to handle the cost versus performance. Okay, because that 5% CPU cycle might be that adapter is more expensive. That adapter and switch more expensive for compared to B. So from an absolute performance point of view, A will be good. But when you take a look at cost performance, that might be different. We'll get into all these things. So that is the system area network. You also need good storage area network. You also need good wide area network. I showed some examples like systems are also expanding, not just within a building, across the building, within a city, across states. So you also need good wide area network connectivity. There is also a need for quality of service. Okay. So just imagine, I'm sure, like, I mean, of course, we are doing this conference virtually this year. Otherwise, all of us should have traveled to the Bay Area. When you travel in the flights, you know, people have different kinds of medallion status. You can have a silver, gold, platinum, diamond. You get different kinds of services. Similar things are happening with e-commerce. So if you are a frequent purchaser or a buyer of Amazon, as soon as you log on, the system will identify, oh, you are a diamond buyer. So your request will get moved much more faster. Or so that is the kind of the new generation quality of service is coming into play. So the question is, if I try to provide that at the network level, then how do you build that easily on top of the other layers? Then, of course, RAS, reliability, availability, and serviceability. This is also very important. If you go back again, I'll say 20 years, 30 years, the general concepts used to be, yeah, if system fails, we'll fix it in the night. All right. But these days, there is no concept of a night. I mean, all these data centers, supercomputing centers are totally operating 24/7, 365 days. And many times you should be hearing some stories, even if like one data center gets shut down for 1 hour, somebody loses millions of dollars in business. So that means while the system is running, you may need to, if the components fail, you may need to fix those things. So that means the networking environment need to provide this kind of a reliability, availability, and serviceability. So all these are good features. Then the question, as I was indicating, what cost? Okay. So because it's a commodity component, just like cars or refrigerators or microwaves, there are so many products in the market, and each one has its performance, features, then also the cost. And there are different ranges of users or customers. They try to choose which one is good for them. And that is exactly the same thing is happening with respect to network. So we'll keep that in mind as we go along. So with that kind of a high level, like 100,000 feet level, let's now go into a little bit of like a 50,000 feet levels. So let's try to take a look at basic architecture, computer architecture 101. I'm sure all of you would have taken these classes somewhere or other. So if you take a look at any of these systems, typically a server, we have a bunch of CPUs, some memory, there's an IO bus, there is a network adapter, there is a network switch. These are the fundamental hardware components. Okay. So then there is a software component, which is the communication stack, which interfaces with all these components to make the system work. So based on how you configure or at any given time, what kind of technologies are available, you may see different kinds of bottlenecks. Okay. And these are purely for communication, not for computation. So for protocol processing, there could be some bottlenecks. There could be IO interface bottlenecks. There could be some network bottlenecks. Okay. We'll go each one of these into a little bit more details. So these kind of bottlenecks artificially limit the network performance the user actually perceives. Okay. It's just like, think of like a car. I mean, car have so many components. Each component might have their own capabilities, but when you put it together, all these components need to work together. So whichever has the limited capability, whichever component, that will determine the overall performance of the car. So same thing will happen in this case for a given server, or in our context for a cluster. So now let's try to go into each one of these components in a little bit more detail, the bottlenecks, and then we'll try to come with the solutions, and we'll see how people are trying to address these bottlenecks. So take a look at like a processing bottlenecks. I mean, it's communication protocols. Anytime you ask somebody, the two things which comes into mind, TCP IP and UDP IP. It has been there from the very beginning of the computer networks. So TCP IP is reliable, UDP IP is unreliable, but it is a generic protocol which was proposed so that I can send data from one node to the other node. But if you go into the TCP IP stack, you will see like there are multiple layers. You would have seen those ISO layers, multiple layers. There are data buffering, integrity, routing aspects. There should be signaling between different layers. So when you go through all those layers, you lose performance, okay? Because somebody has to do those things. So once you go through all these layers, there is overhead. So even if I want to send like a 2 bytes to you, the transmission time may not be taking much, but once you go through the protocol stack overhead on the sender side, the receiver side, or sometimes even the switch, a lot of overhead gets added. So that's what we'll identify as a protocol processing bottlenecks. The second bottleneck is the traditional IO interface. Okay, sometimes this is called like a last mile bottleneck. And these days, as you know, I mean, all of us work with the Zoom and everything. So this is becoming very important. It depends on the what kind of subscription we have for our home. I mean, the internet might have a lot of bandwidth, but the link which comes to our house from our cable providers, that determines the overall performance. Okay, the same thing happens in the server. My processor and memory might be very faster, but the rate at which I can send data in and out, that will determine the overall performance of the system. So in this context, let's go back in the history. Okay, almost 30 years back, this PCI was introduced. Many of you would have heard of this term, peripheral communication interface. So in the 1990s, it used to be a bus. So this bus was defined like a 33 megahertz 32 bit. Okay, so there used to be with 32 bits, and each bit you can flip at 33 megahertz rate. So if you do a quick math, it used to be 1.05 gigabits per second. So that means irrespective of what happens within the node or outside the node, the maximum rate at which you can send data back and forth is 1 gigabits per second. Of course, for 1990s, it was good, but very soon, as you saw in the history, in 5 to 6 years, people found out that that is not good enough. So then PCI-X was introduced. So it tried to increase the 32 bits to 64 bits and 33 megahertz to 133 megahertz. Okay, so there are 2 degrees of freedom. You can multiply both. So then there was a degree of 8 improvement here. So then they improved also further, which led to 17 gigabits per second. There was a V1 and V2. But then since it was a bus, if some of you have the background in the electrical engineering, you will see that when it's a bus and every bit, they're sitting next to each other and every bit is flipping very fast, it will lead to a lot of crosstalks. Okay, it's just like, you know, in a house, if 5 people are talking with the wireless, you will generate a lot of crosstalks, and that's exactly happens on the system. So there will be skews between the wires. So the signal integrity will go down in this design. So that's what people found out, that you cannot just keep on increasing like this to get higher bandwidth. And again, in few slides, we'll see how to resolve that. So then the third one is the network bottlenecks. Okay, so even if I design the system properly, what happens outside? Okay, so here again, if you take a look at the Ethernet, it started in 1979. It started with 10 megabits per second, and the world was very happy for 14 years. Okay, nobody needed a higher speed. Okay, because if you go back 1979, it was very new. Internet was only used for like some DARPA, ARPA, people to exchange emails or documents. There was no computing involved over the network. Okay, so then, but gradually things started, and fast Ethernet came, gigabit Ethernet came. There was a technology here called ATM. If some of the old timers, including me, know that, we work on that. It is not the bank ATM, it is called asynchronous transfer mode. So a lot of knowledge came from the networking side, like, the telecommunication side. Those technologies tried to come to the computer networking side, but it didn't actually pan out very nicely. It got dead. People renamed that, called another terrible mistake. Okay, that's what was identified at the end when ATM died. But then in 1993, this was the very first generation of real cluster computing came. Some of you might have heard of a company called Miricom. So they introduced MiriNet. So this was the first commodity networking technology you can actually buy. And those days it would be Solaris servers. So you can actually buy the servers, buy a switch from Miricom, some adapters, you can put them together to build your own cluster. So that's how the cluster computing started, with 1 gigabits per second. And gradually storage networking came and the fiber channel came to the market. So as you can see, from 1979 to 1994, there was the bottleneck also tried to got alleviated. So those are the past. So then there was a lot of discussion saying, okay, how do we move forward? And this is where you can think of the birth time, I'll say, not the birthplace, birth time for InfiniBand and high-speed Ethernet. So this is where the industry people started thinking that how we can solve all these three bottlenecks: protocol processing, IO bus, and networking speed. Okay. And of course, Ethernet was already there, as we saw, but InfiniBand was a newer technology. Okay. So Ethernet aimed at directly handling the network speed bottleneck, but trying to alleviate the protocol processing and IO bus bottlenecks in a complementary fashion. But since InfiniBand was totally new, they were able to make a lot of changes that had some advantages, but very soon we'll introduce, there were some also issues. Okay, we'll go over that. Any questions so far? Any quick question? We are still at like a 50,000 feet level. We'll gradually go down. Any quick questions from anybody? Please feel free to ask questions on the chat or post it on the Slack. I think Hari, I believe you are monitoring the Slack channel.
Yes, I'm monitoring the Slack and the chat.
Yes. Okay. So with that kind of a background, let's move ahead. So Infiniband. So this is where the Infiniband association was formed with 7 industry leaders. Some of them are still not there now. They have been acquired by other companies. But if you read this goal, the goal was to design a scalable and high performance communication and IO architecture by taking an integrated view of computing, networking, and storage technology. So it was not just a networking technology. They wanted to take a global look how these systems need to be deployed. And based on that, these standards were identified. So the volume 1, version 1 actually was released on October 24, 2000, almost 21 years back. And then, of course, as the systems kept on being deployed, the standards, people found out some limitations, people saw some issues. So then gradually several annexes were introduced, like Rdma CM came in September 06, ISER, XRC, Rocky. We'll cover some of these things. So the latest version is actually available on the, it was released on April 2020, is the 1.4. So if you go to this site, Infiniband Trade Association, you should be able to download this entire specification. Okay. But be aware, it is not a few pages of document. The Infiniband, if you download it, 1700 pages document. Okay. Because it's a purely networking technology standard. You can design your own adapter, switches, they should be able to talk to each other. So it is 1700 pages. Of course, we'll not have time to cover all those 1700 pages here, but we'll try to give you some highlights. So that means you will be able to at least know the basic terminologies. And we typically do an advanced version. Of course, in the hot eye, because of the limited slots, we don't do that. We'll be offering this one as well as the advanced one at supercomputing in November. So if some of you are interested, you are welcome to join those. So there we go into a lot of additional concepts in this technology. So today we only have 3 hours. So we'll try to cover the things in a lossless manner, the knowledge, so that you get the idea at a high level. So once Infiniband was introduced, the similar things also happened with the high-speed Ethernet consortium. There was a 10 gig alliance was formed. The goal was very similar, to achieve a scalable and high-performance communication architecture while maintaining backward compatibility with Ethernet. Now, then what happened? In the beginning, it started with 10 gig, but gradually multiple things happened. So if in an Ethernet world, if you always see it's a multiple of 10, like a 10 megabit, 100 megabits, 1 gigabits, 10 gigabits, the natural progression was to move from 10 to 100. But now the thing is, if you just want to now take a look at those 3 bottlenecks, if I just want to increase the network speed from 10 gig to 100 gig, will it work? Because if the IO interface is not matured enough, it will not work. And that's what exactly happened. So we'll go into the next few slides in more details. But during that time, Infiniband had gone into, I'll introduce very soon, called a QDR technology, quad data rate, which was supporting 40 gigabits per second, Infiniband. So then the Ethernet consortium wanted to take advantage of that. So that's why an intermediate version was introduced called 40 gig. It was like a lot of debates, and then there was a voting took place to introduce that 40 gig. But then gradually what happened, 40 gig was also becoming very expensive. And since Infiniband and Ethernet were following a very similar kind of a cable structures, they wanted to use the similar kind of a infrastructure. So nowadays it has been also intermediate version has come, 25 gig. Okay, we'll see it very soon why that is done. So nowadays Ethernet is available 25, 40, 50, 100, 200, a range of speeds are available. Okay, and many of these components actually match with the corresponding Infiniband speed. And these are the pointers I'm trying to provide here so that you can take a look at these. Ethernet also has a lot of focus on energy efficient, power conscious protocols, on the fly speed reduction. And of course, looking forward, there's a lot of discussion taking place on the Ethernet Alliance to move it into the terabits per second. So now let's see with both the InfiniBand and high-speed Ethernet, how they wanted to handle these bottlenecks, because we talked about these bottlenecks, but now let's see their solutions. So the InfiniBand, if some of you have not been aware, it's actually a word. It's not an acronym, but what they tried to combine two words, infinite bandwidth. That's how the name came into the picture. Infinite bandwidth, they put it together called InfiniBand. So what really means by infinite bandwidth? So we talked about the bus earlier. So instead of the bus, what InfiniBand introduced called independent pairs of wires. Okay. So instead of a bus, I'll have independent pairs of wires to transmit independent data. Okay. So this is called bit serial differential signaling. Okay. So we'll call it like one such pair is called a lane. Okay. Then I can have any number of lanes, and each lane is like a twisted pair. It is shielded. So there will not be any crosstalk. So I can have multiple of such lanes. And now then I again have 2 degrees of freedom. I can keep on increasing the number of lanes, and I can keep on increasing the clock speed of the lanes. Okay, because each lane consists of only a pair of bars. So now we still have those 2 degrees of freedom, but next slide, I'll show some numbers. Continuously as the demand increases, people can play with all these 2 parameters to go with higher and higher bandwidth. So theoretically, there is no perceived limit on the bandwidth, and that's why the name comes as a InfiniBand. Okay. So now let's take a look at this in a more concrete manner. So this is what we had seen up to 1994. InfiniBand, the standard got introduced in October 2000, but the product started coming in 2001. So at that time, it used to be called SDR, single data rate. So that means if I have a clock, I send 1 bit per clock. And then the speed was on the clock at a physical layer, it used to be 2.5 gigabits per second. And they have the 8 to 10 encoding. So here we are like, since we are referring across all the different networking technology, we are only showing the payload data, not the physical speed. So 2.5 with the 8 to 10 encoding will lead to 2 gigabits per second payload. Okay, so this is used to be called one lane. Okay, and in the 2001 also 10 gigabit was introduced. But as the demand increases, now in the 2003, you see that SDR remained, but instead of 1 lane, 4 lanes were introduced. In a single cable, 4 lanes were introduced. Now you can see you can jump from 2 to 8 gigabits per second. So then in the another 2 years, there was a need for another higher bandwidth. So what they did is SDR, it moved to DDR. That means double data rate. That means in the same clock, I can send 2 bits. That is like increasing the clock speed for every lane. One in the upper end, upper clock, and another is a lower clock. So now you can see you get another 2 factor of 2 improvement. So 16 gigabits per second. And during that time, 2005, in fact, almost 16 years back, IBM introduced their own InfiniBand thing. It was using SDR, but it used 12 such lanes. So if some of you remember or have used this technology, the cable was very thick, okay, because 12 such twisted pairs are combined together, and it was able to give 24 gigabits per second. It was very high in the performance, but these cables were so strong or so heavy, there was a lot of reliability issue. If some of you are familiar with how the clusters get designed, you have a server, the network adapter is sitting like this or sitting like this. And if the cable is so heavy, it tries to bend. So there was a lot of reliability issues. So that actually couldn't fly. So that got decommissioned. But then interestingly, what happened in another 2 years, this DDR got moved to QDR, quad data rate. So in 1 clock cycle, the technology allowed to send 4 bits. So now we got another factor of 2 improvement, 32 gigabits per second, and the physical was 40 gigs. So this is where that 40 gigabit Ethernet was introduced, because IO interface was already supporting at that rate. So then what happened in another 4 years, this QDR moved to FDR. This was very interesting. it's an odd number, QDR. It should have been a ODR or OCT, but they were able to send 14 bits, okay, per clock. And then at the same time, another innovation happened. If you remember here, I said 8 to 10 encoding, but they came up with the community of the encoding community came up with a better encoding scheme, which was 64 to 66. Okay, so instead of like losing 25% of the bandwidth, they were able to cut it down. So with a 64 bit, you only needed another 2 bits for the parity, error checking, recovery kind of things. So if you do a quick math, that was the first time in 2011 they were able to deliver with 4 lanes 54.6 gigabits per second. And then if you use one network with 2 ports, and if you do a channel bonding, in the next year, they were able to deliver 100 gigabits per second. And then in each one of those lanes, that became very similar to Ethernet. So this is where that 25 and 50 gigabits per second got introduced in 2015. Instead of FDR, it went to like Ethernet was introduced 100 gigabits. And then Omnipath came into the picture, and we'll talk about this. Omnipath, many of you must have heard of this term in the last several years, but it has its roots in the InfiniBand. It used to be from company QLogic and all that was acquired by Intel, and they renamed that to the product Omnipath. So again, InfiniBand got into different versions. So Omnipath was introduced, then InfiniBand 2015 was the EDR, then HDR got introduced in 2017. So as you can see, just even 2001 to 2017, in 16 years, the network bandwidth improved by a factor of 100. Okay, and of course that trend continues. There are all these. This is the roadmap, the slide taken from the InfiniBand Trade Association. These are NDR, XDR, GDR. They have been introduced, and very recently, in fact, they have removed all these names. You can talk to the InfiniBand consortium people, but now they want to keep it open and use the when a new technology comes, they want to define it like a 400, 800. Or 1.6 instead of the names. I used to mention earlier, like, English alphabet has 26 alphabets. So there is a lot of opportunities for growth. We have just taken only S, D, Q, F, E, H. A lot of characters are still left. Okay, one can come up with those speeds. Any questions here? This is one of the fundamental components to understand how the networking technology is evolving. Is the concept clear? The InfiniBand, infinite bandwidth concept. Okay, thanks, Arun. So again, please feel free to ask questions. So then we'll try to be more instead of just talking in a monologue fashion, we can actually have discussion. So next, let's think of protocol processing bottleneck. So the protocol processing bottleneck. So here the idea is that, as we saw earlier, like the TCP/IP has a lot of overhead. So then gradually people started asking questions, can we have intelligent network interface cards? So here I'll try to introduce the concepts of executives and secretaries. Just like in our offices, I'm sure many of you are managers, you have secretaries. So for many regular works, you offload to the secretary. Let's say, okay, set up the meeting, take this printout, send these emails. Of course, you can do it. But if you offload to the secretary, then you can actually have more cycles to do decision making. So similar ideas, let's bring it to the clusters. The processors are executives and the network cards are secretaries. So instead of the processor doing all the things, like the CPU doing everything, can we offload some functionalities, communication and IO functionalities to the secretaries? If we can do that, then we'll have a lot of advanced designs. And this is what started, in fact, in the mid-90s. And this is where gradually, people started with different solutions. We'll see some of these examples. People even try to offload the entire protocol processing complete in the hardware. But then the question is how they communicate with each other. If you have an established secretary for 10 years, even you don't have to talk. You just say, okay, today is this date. The secretary knows what to do. Okay. So that means these are rich user level communication capability. We'll introduce that. It gets rid of a lot of intermediate data buffering, all those software signaling, so that when we send the data, it really happens very fast and you get the good performance. So then the third thing happened with the IO interface technologies. So as I said few slides back, when Infiniband came in 2000, they totally went with this bit serial differential signaling. Okay. But then the idea is that if I want to get data from, let's say I have a server, two servers, a sender memory to memory, I need to send the data, not adapter to adapter. So Infiniband started proposing saying the PCI bus also needs to be replaced. Okay. But of course, that didn't play very well with vendors like Intel, who has the proprietary things happening on the front side bus and all those things. So there was in the mid 1990s, you can do a search on the archives. There was a lot of fight, even though Intel was a part of the Infiniband in the beginning, but just like in the Bay Area, I mean, many companies work together to come up with newer consortium, newer standards, but the bottom line is the revenue. If you don't get revenue and you see that you are losing your current products, you try to kill it. And that's what exactly happened in mid 90s. Intel tried to withdraw from Infiniband. But then what was happening, Infiniband was not only the technology, that time the GPU technology was also evolving. NVIDIA technology with GPU, CUDA was just coming up, and they also had the same problem. Like if I connect a GPU to CPU over PCI, PCI was the bottleneck. Okay, how do I take data back and forth between the GPUs? So Intel was being banged from both the sides, from the networking field and from the GPU field. And I just want to quote here, as you know, this is also another Bay Area company principle. If you cannot win fighting with the enemies, what do? You join with the enemies, come up with something new. That's what happened. So Intel then, instead of sticking to the PCI, the standard PCI, they introduced the PCI Express, okay, which is very common, but that's how the history, if you see here, 2003, this was like a PCI X we had seen up to 2003. Then the PCI Express was introduced, and they borrowed exactly the same ideas like Infiniband. Okay, so that means you will have some number of lanes, and each lane can have some speed. So that means each one is a 2 gigabits per second lane. If I have 4 such lanes, I can have 8 gigabits, 16, and then 32 gigabits. And then over the years, as the demand has come more and more, PCI Express also has been evolving, Gen 1, Gen 2, Gen 3. But then what happened, the world was very happy, but again, another fighting started here in the last few years. We'll see because of the Omnipath being acquired by from QLogic and Omnipath being introduced by Intel, they wanted to compete with Infiniband, and they deliberately tried to slow down this Gen 4. So unless you get Gen 4, here you will see that you cannot even go to, unless you have a 16 channels, you cannot go to 100 gigabits or 200 gigabits per second. Okay, and that actually led to NVIDIA coming up with the NV links. Okay, because this is how the Summit system and all got developed with NVIDIA, with Mellanox, with IBM, with a proprietary network called, because they didn't want to depend on the PCI. So like this, over the years, we are seeing all these different trends, but IO interface is an important factor. And currently, most of the systems are using the PCI Express, except some of the NVIDIA systems, they have the NVLink, but some of the systems have both also NVLink and PCIe. But what it means that if you have a network, this is the key point from this slide, you need to make sure that all of them work together. So for example, if I have a motherboard with 8x Gen 4, I cannot put a 200 gigabits per second Infiniband. Okay, that is a bad configuration. Okay, so you need to match, you need to have at least 16 channels of Gen 4, so then you can match the 200 gigabits per second. So as a system designer, or if you are acquiring some cluster, you need to take a look at some of these things. Okay, otherwise you will be paying money, but in the end, when you assemble these systems, they will not work. Okay, any questions here on this aspect? Things are fine, everybody's awake?
I had a question.
Sure.
Sharon here.
Yeah, sure.
At the line where you talked 2009, Why do you say approximate 32 gig or approximate?
Yeah, because here what happens, the PCI, the PCI has its own, like there are some control packets which go around. So depending on those, the implementation, you may lose a little bit. Okay, so that's why we have just put approximate.
And a second different question on QPI.
Yeah.
I always viewed this as something that would be kind of like on the silicon chip or motherboard itself.
Yes.
QPI was not external.
I know. So that's why I'm just coming to that. So these are the outside. So then what happened, the two of these, as the multi-core technology have been evolving, so there are two technology being used. One is the Amd Hyper Transport. So that means I have 128 cores within a node, or let's say 64 cores within the socket. How do I connect? Okay. So AMD has this Hyper Transport, and Intel has the same thing on their chip, which is called QPI. So these days, what happens if you send, let's say, data from one processor or one CPU core of a node, a CPU core up to the another node, it goes through multiple hops. First, it goes through, let's say, it's an Intel system. It goes through QPI, then it goes through Infiniband. I'm just saying, giving an example, or it could be Ethernet or any of them. Then again, going back to the adapter and going back to the QPI. So that's how the end-to-end works. Is that clear, Saran? Okay, so then this is where, again, a lot of actions are taking place, and even in the Hot Eye conference, you heard some of these things. So people are trying to ask the next generation. We are talking about exascale systems. We want this communication overhead to be very small. So I talked about NVLink. IBM and all has been focusing on OpenCAPI. HP has something called GenG. So they're actually trying to take, Sharon, just like to your. So this is a network. This is a network which can actually go from within the node even to the outside. Okay, so you can see the GenG here, and then this CCIX is the cache coherent interconnect. So a lot of these things, I think the CXL also fits into this domain. We have not listed it here, but the objective is very also similar. Okay, so people are always continuously innovating these interface aspects together with the outside network. Okay, so with that kind of a background, now let's take a look at one such thing, Infiniband, which is very common. I think there was a question here. Can you share some details about OMI interface, which is serial link under OpenCAPI? Unfortunately, I don't have any information. Hari, do you have that, or we can follow up with you later on?
We can follow up offline.
Yeah, thanks. So now let's take a look at Infiniband and what we'll try to do. And these ideas will be very similar to other networks. So that's why we are starting with Infiniband, because this has become very common. A lot of people have access to these clusters, or some of them also might have used it. And once you understand for one technology, you can take the concepts into multiple technologies. So I'll consider first some Infiniband architecture, communication model, semantics, and then we'll go into the Ethernet family. Then we'll try to take a look at the convergence. So every time a new networking technology comes, always people try to relate back to the Ethernet. Okay, so let's start with that. So traditional Ethernet, since all of us have been trained in these or taken some courses somewhere, we can relate very easily. Ethernet has the physical layer, link layer, transport layer, network, transport, and application. So if you see here, like a physical layer, it can be a copper, optical, wireless. Link layer, typically there is some flow control, error detection. Those are the responsibilities of the link layer. Between the network layer and link layer, there are typically some DNS management tools. And the network layer takes care of routing. And transport layer, this is very important. Most of the applications in the Ethernet world are written with sockets. Any applications you have at the underlying, whether it is HTTP, FTP, MPI, storage, cloud, or file system, you go down, the communication is over sockets. Okay, so that is the link to the lower layers. And typically, the sockets have two such transport options, TCP or UDP. I mentioned that earlier. TCP is the reliable, UDP is unreliable. So that's how the Ethernet world. So when Infiniband came, we can exactly try to map. Infiniband has copper or optical. It doesn't have wireless yet. Link layer takes care of the flow control and error detection. So just like DNS management tool, we'll introduce this concept called Subnet Manager or called OpenSM, which is the open source version of that. That's like the management tool, very widely used. Network layer takes care of the routing. And in the beginning, corresponding to TCP UDP, Infiniband also introduced two of these called RC, which is reliable connection, and UD, which is unreliable connection. But the major difference was here, and that's what we'll spend some time, because you remember we talked about this user level communications, intelligent adapters. So if you go through sockets, there is a lot of overhead. So this is where they introduced a new kind of, they called verbs. So think of it as a very low level communication, just like you talking to your secretary with a very common terminologies, okay, to make things much more faster. And then these applications, if you want to get good performance, you need to talk to verbs. Okay, so with that kind of a very high level overview, let's try to now see in a pictorial manner. Okay, and we'll continue the slides. We'll see after you reach some another 30-40 slides, you'll get a very complete picture of all the different networking technologies and their implications. So let's start with this. So this is the standard TCP IP stack. So if you go to the left side, this is like an Ethernet switch, Ethernet adapter, and we talked about like TCP IP. Any application is written with the sockets. It goes to the TCP IP, but it goes through the kernel space. Okay, and this is where all this performance overhead comes. And this is a pure left column is like a Ethernet, 1 gig to 100 gig or even 200, 400 kind of things. And when Infiniband started, or any new networking technology comes into the market, they always try to provide a backward a path. Okay, so that means even the sockets application can run. And in the Infiniband, it's called IP over IB. Okay, IP emulation over Infiniband. So that means if you have some sockets based application, you should be able to run it. You may not get the best performance. Over the years, IP over IB has improved significantly in terms of bandwidth, but latency still has some overhead. So that's how like you can still run the sockets application. What Infiniband proposed 20 years back, and we'll spend some more time on this, is an Infiniband adapter, Infiniband switch. This is where that RDMA, remote DMA concepts came. Okay, most of you are familiar with the DMA. That means DMA has been there from the beginning of the computing technologies. Within a node, DMA is used to transfer data from memory to IO or IO to memory. Okay, but of course CPU can do it. I can write a program which will continuously do load store, load from memory, store to the IO, or load from memory, load from IO to store to the memory. But then my CPU will be continuously busy, and it will not have any cycles to do the computation. So that's how the DMA was invented. What Infiniband did, it extended to remote. So that means the same idea that I can move data from a memory of one node to the memory of other node with very little involvement from the sender and receiver side. And we'll see how that gets done. Okay, this is a very key concept. In the next few slides, we'll expand that. And that is also linked with this user space protocol with intelligent cards. All of them work together. But then there was a bottleneck that in order to use this kind of functionalities, the sockets will not work. So that means either the middleware or the application needs to be rewritten. Okay, so take an example of an Mpi library. So Mpi library can run with sockets, but Mpi library needs to be redesigned to get good performance with bursts. Okay, so in 2000 there was no such Mpi library. We were the very first one in my group to come up with the Mpi library. We'll talk about that later on. In 2002 we had the first release, and continuously over the years a lot of other Mpi libraries have moved to this path. Okay, even a lot of newer network technologies have also adopted this RDMA. Okay, so this is very common on the modern day systems. So here I said application / middleware. So that means if your API is enhanced, the end application can still run without any changes. So same thing about file system, same thing about the storage, same thing with the cloud, big data. So somewhere in the middleware layer, you need to make those changes. So now let's see this right-hand side, how that works, not only for Infiniband or for Rocky or for any of the modern things. So before that, let's go into some of the components. Infiniband, you know, the hardware wise, like a channel adapter. This is just like a Infiniband adapter. If you take a look, it is just like any other network adapter. It has a bunch of ports. There are some virtual lanes we'll talk about a little bit later. They have some programmable DM engines. The idea is to move data from memory to IO or IO to memory. In a strict Infiniband terminology, it is known as HCA, or a host channel adapter. So then if you're trying to deploy system, you need also switches, and sometimes you may need routers. So there are a little bit of differences. The switches is within the subnet. It's just like, Ethernet. We have a subnet. You typically go through like a 90.10.2.5, like that is a subnet. Then you have multiple of such subnets connected. Same idea works here. So within a small cluster, you can have a subnet. So then you just trying to do switching. You don't do routing. But if I want to send a data from, let's say, this node to this node, and they are across different subnets, then I need routers. Okay. So first I get routed to the edge node, edge router, and then from there I again get routed to the other node. And in addition to point-to-point unicast, Infiniband also has multicast. Okay. So that means at a switch level, if I push the data, hardware-wise, it gets replicated. And that actually helps a lot for very large scale systems, enhancing collectives like broadcast and other related collectives, and that has a big impact on the overall performance. So then we have the components, links, and repeaters. I talked about copper, optical, even for some of the blade servers. Infiniband provides the PCB on the backplane. They are not directly addressable. So in the beginning, Infiniband started with copper cabling, but since it is a hot interconnect conference, I'm sure many of you know there is always a trade-off, speed versus the length. So when Infiniband in the SDR, it was good, copper was good, but once you started moving to QDR, the people found out that there is a lots of signal integrity issues if it crosses 7 meters. Okay, so at that time, Intel actually came up with the very first optical cable, copper to optical conversion. So as you can see, with very little overhead. So for example, this is electronics, it gets converted to optics. On the other end, it gets converted to electronics, only 550 picoseconds. Okay, so effectively, you don't see any much difference. And then once that came, over the years now, you get both copper and optical. Of course, optical cables are more expensive, but typically people try to do within the rack, they use coppers. This goes to the top of the rack switch or the TOR, and then across the top of the rack switches, you used optics. And there are a lot of solutions from all different vendors. Depending on your system size and all, you can come up with a good configuration, how many copper cables you need to use or how many optical cables you need to use. In the Infiniband specification, there is actually a very separate volume 2. Okay, we'll not talk about these. I mean, it exactly tells like the length of each of the pins, the sockets, everything. So if you are trying to design those kind of cables interfaces, you need to take a look at those volumes. But the more important thing is the communication model. I think that is very much important to understand all the modern high performance networks. So let me go into that a little bit more detail. So here, if you see, this is like a Infiniband or even some of the modern networks, they combine all these things: transport layer, network layer, link layer, physical layer, all this functionality into their adapter. So this is where you have intelligent network adapter. Okay. So then from the top level, these are the Infiniband terminology. We'll gradually introduce few of them. So like the CPU wants to send the data, it has to inform the NIC. Then the message actually goes over the network. Then in the receiver side, you get the data. So again, goes back. So before we understand how the data goes, let's try to understand the communication semantics, like what the user expects from these systems. So in this context, there are two models. One is called a two-sided communication model and another is called a one-sided communication model. So we'll go into both. So two-sided communication model, before I go here, similarities are like our emails. Okay, so think of our emails. I send you an email. You have your own mailbox. My mail can go to you, but unless you open your mailbox, you will not be able to read it. So that's why you have to participate. Okay, and at the same time, not now, but many years back, if you remember, the technology was not strong. If I send you a huge file, you will get a message saying message is rejected. Okay, these days, of course, mail servers have a lot of memory. You don't see that message, but the Infiniband network, same thing can happen. Okay, so typically what happens in this two-sided communication in the Infiniband or any of the high performance network adapter, before I receive a message, I need to post some buffer. Okay, so for example, here is a P2 is expecting some message from P1 and P3. It posts two buffers and then continuously polls. Okay, especially in the high performance. If we are looking at a high performance application, you know, latency is very important. So instead of going through interrupt, I do polling. So continuously the receiver adapter polls, and then the same thing happens like as let's say the sender is ready to post the send, see the animation, the adapter sends, and then immediately the receiver knows that a data has come and it receives the data from P3. Same thing can happen from P1. So this is a two-sided model. As you can see, from the data to move from memory of sender to memory of the receiver, both sender and receiver are participating, actively participating. This is a two-sided model. On the other hand, there is a one-sided model. So this comes very similar to the Rdma, or rather Rdma helps to achieve this one-sided communication. So the idea here is a real life example is like a trusted friend. Okay, so let's say you have your colleague in the other office. If you want to take a book from his or her office, if you have a trust, the friend can tell you, oh, at any time you can come to enter to my office. You don't have to knock on my door. Come in and get my date, take the book. After you finish, put it back. So similar ideas, we want to bring it to the network here. So in the one-sided, what happens, typically most of the applications have some procedure called initialization. It is there in the MPI called MPI init. Most of the middlewares have that. So during that time, you can actually do some global region creation. You can do some buffer information exchange. So I can allow you to write to my memory. Another node can allow me to write to his or her memory. So like this, a lot of information get exchanged. But then after that, if I want to really, in this case, write or a put operation, as you can see, directly I can do this operation. As soon as I write to the SCA, it goes there and gets written to the memory. We'll see a detailed animation in the next few slides. But the idea here is that I want to cut down all those overheads. The two-sided, I don't need synchronization. I don't need those buffering, etc. I want the best performance. So this is where the one-sided communication comes. So in that context, what Infiniband has something called a queue pair model. Okay. So that means if I want to communicate, I have a send a queue, I have a receive queue. Just think of it's like a secretary's, secretary's desk. There is an incoming desk outside going. So the idea is very similar. So then what happens, I submit these queues, the processors are submitting work request, the adapter or the secretary is taking all these work queues, perform those operations and inform the executive. Okay, so in the Infiniband terminology, it's called UKI, like a work request being posted, and then called cookies, which are taken as for the completion of those events. So broadly, you keep on posting cookies, keep on receiving post cookies, receive cookies. That's how the Infiniband terminology works to send the data. But then, how about that overhead we talked about, user level communication? So as you know, most of the time in the modern day systems, when we write a parallel program or something, it is always I am trying to write the program in the sequential program in a virtual address space. But when we go down to the real communication, let's say you have a DMA, you need to program, you need to give physical address. So there is a disconnection here. Okay, so what happens if I want to send some data and it's not available in my memory, physical memory? So you will be encountering a lot of overhead. So to alleviate that, what Infiniband consortium did, and all the other modern network also do that, before you do communication, all memory used for communication must be registered. Okay, so that means you send a registration request, you send virtual address and length. Now what happens, the kernel handles the virtual to physical mapping. Okay, this is very important because you don't want the user process to do this because of the security. Okay, and in addition, while this address translation is taking place, the HCA or the adapter caches that virtual to physical mapping and issues a handle. And that handle has actually two parts. One is the local key, which comes back to this own processor, and another is a remote key, if anybody else wants to write to my memory, I need to send that remote key. Okay. And once you do this, the registration is finished. Registration takes a lot of time. Over the years, Infiniband consortium is trying to improve on that registration, but still there is a lot of overhead there. But once it is done, excuse me, when you try to sending the data from that registered buffer, then what happens? Your process directly tries to send the data with a L key. So you present the data, you present your key, SCA verifies that it is correct, and then sends the data out. Okay. And as you can see in this figure, this is not going through the kernel. Earlier, if you remember, like everything was going through the kernel. So this is word called kernel bypass or OS bypass. There are multiple terminologies in the literature. User level communication, kernel bypass communication, OS bypass communication. But the broad idea is here that when I'm doing the data transfer, it doesn't touch the kernel. That's why we are able to get that microsecond level benefit performance. Okay. And this is for the local key to send data. I talked about that one-sided model. The same thing, somebody, if he's trying to write to my memory, in addition to the data, the R key needs to be presented for RDMA operation. And originally for the R key, it was actually not encrypted in the Infiniband. The idea was that it is within a building, so that unless you get physical access to the system, you'll not be able to tamper it. But nowadays, you know, Infiniband is also going wide area network, but those routers have actually R key encrypted. So those routers are very expensive, but they do the encryption at the line rate so that you can actually have RDMA protocols over wide area network without violating any security. So let's put all these things together. Some of my students and all, we have put together very nice slides. It'll give you the complete picture. Okay. So we'll start with the send receive model. Take all the knowledge from there. Here is an animation. So this is the sender side. This is the receiver side. These are our executive, the processors. This is the secretaries. So in the beginning, before we communicate, as we said, the receiver has to post a buffer. Okay. Saying that, yeah, I'm expecting this data from somebody. So this wiki will have information on incoming messages, where to, if the message comes, where to put it in the memory. Sender side, it will try to do very similar things. From the processor, it will try to post a wiki. This contains information about the send buffer. It could be a contiguous, it could be multiple non-contiguous. Once you do that, then it is the processors are done. They don't have to do anything else. Now you can see the executive or the secretary will go pick up a wiki, go to the memory, fetch the data, send the data over the network, go through all those network layer, transport layer, everything. But then the problem happens, this is the two-sided, because even though message has reached the receiver, it doesn't know where to be placed. So this is where a matching will take place. Okay, that wiki which came, there will be a matching saying that, oh, this wiki said that if I get a message from processor 1, I should put it somewhere. So then after that, it will go and post the data into the thing. And then after that, it will generate a cookie. And we talked about the cookie can be pulled or it can be interrupted. There are multiple such solutions available. And then you send a hardware act back. Sender side also gets a cookie, and the sender knows that the data has reached the receiver. So this is the typical two-sided protocol. So now you see, I talked about CPU utilization, you remember earlier. So if you put all these things together, you will see that the processor is involved only to post receive wiki, post send wiki, and pulling out completed cookies. That's all. Processor is actually not doing any kernel level operation, or not doing buffering, or not doing packetizing, which happens in the traditional TCP/IP sockets. So that's why the CPU utilization is very low. As I said earlier, like a 5% kind of thing. So it's very low. Sometimes even it can go also even lower. So that is the strength of all these intelligent network adapters. Okay. So now let's try to take that into the RDMA. Okay. So in the RDMA, now we'll see the next level. So as we discussed, the RDMA, it's a one-sided model. It will try to utilize. So the receiver doesn't have to post anything in the beginning. As you see, sender only posts the thing, wiki. But now this wiki has more information. it not only has information about the sender buffer, it has information about the receiver buffer also. That means once the message reaches the receiver, where it will be placed, you will see the animation. It doesn't need to synchronize, or it doesn't need to do any matching. Okay. So, so it will get the message, and then you see, let me repeat it. It will get it, go over the networks, go through the adapter, and directly gets written to the memory. And then the remaining steps, you will get a hardware act, you get a cookie. There are different mechanisms here also to identify whether the receive has come or not. There are, like, you may monitor the last byte. Mellanox provides a very strict ordering. You can monitor for the last byte, or you can send a follow-up short messages to generate interrupt. So there are different procedures to know that the message has come. So this is called a RDMA write or RDMA put operation. So now if you see, the initiator processor is involved only to post send cookie, pulling out completion cookie. There is no involvement from the target processor at all. Okay, so that is the most strength of this RDMA model. Okay, so that means if you write your middleware properly, or if you do an intelligent design, your receiver processors can be continuously computing, and data can go in and out without taking a lot of CPU cycles, and that leads to overlap of computation with communication, and that leads to good performance. So this is where all the modern high performance networking technologies are heading. Okay. Now here I give a real life example. Some of you can correlate. So the idea is very similar. Let's say I'm trying to write a proposal. All of us write papers, proposals. We have deadlines. Let's say I have a deadline today at 9 o'clock. I'm getting hungry. So the question is, do I step out and grab my food? In that case, I'll be spending, as a CPU, will be spending some time. Okay. But on the other hand, if my spouse or my child brings the food to my table, or my friend, I can keep on working and while biting my food. Okay. And that is RDMA delivered food you can think of in a loose term. So that means I'm able to overlap the communication, the food delivery with my computation. Okay. And that's what exactly is happening all in these modern networks and modern middleware. So when people say that, okay, I need to enhance this middleware for RDMA, it is not just changing the send receives to some RDMA. You need to totally rethink the structure, or how the code needs to be rewritten so that you get this overlap of computation with communication. So then similarly, the Infiniband also introduced atomics. So earlier we just talked about the point-to-point, but there are a lot of atomics operation which are very widely used, like fetch and add, compare and swap. Earlier, solutions were available within the node over shared memory, but the solutions were not available outside the nodes. And you need to, for example, if I have a single variable and two of them are trying to do fetch and add, we need to make sure that they are done in an atomic manner. Otherwise, the status will be unknown. So Infiniband tried to provide that. So here you will see this like a fetch and add. So what I try to do, this message goes here, and it actually gets the data from the memory and performs the operation. So this was the very initial stage where the network adapter, instead of sending the data, they also wanted to do computation involved. Okay. And after you do this computation, you send the things back to both of them. Okay. So this is like a compare and swap. You can do a fetch and add, and this kind of mechanisms helps quite a lot in providing distributed locks, semaphores, and it helps to cut down on a lot of synchronization overhead. So this was the early phase when the Infiniband adapter had computation capabilities, but now we'll not be covering it in this tutorial. We cover that in the advanced tutorial. The in-network computing, you might be hearing a lot. People have, Mellanox has started pushing computation into the switches, computation into the adapter, and then the next generation, the DPU technology. If you know, the data processing unit is having ARM cores in the adapter, in fact, perform also computation and offloads a lot of communications. So those are a lot of interesting things moving around. I mean, you heard some of those things in even in the hot interconnect. From our group, we are very actively working on that. We had actually a paper presented by one of my students trying to take advantage of this intelligent adapter, the DPUs, for deep learning. How do you accelerate deep learning? And next week actually is we have a Mpi user group meeting. If some of you are not familiar, Hari will post the link. We have a 3 days program, and then you will see there are a lot of vendors and all will be presenting results on the very latest on the MPI technologies, cloud technologies. How do you take advantage of all these high performance interconnect? So, so that event is free. If some of you are, it is happening virtually. If some of you are interested, please feel free to join, and you will see a lot of get a lot of newer ideas there. So with this, let me take a pause here. If there are any quick questions, we'll be very happy to answer, and then here I'll transfer to Hari. He will try to cover some of the remaining parts. You are muted, Hari. You are muted.
Yeah, thanks, Dr. Panda. Hi all. Are you able to see my slides?
Yes.
Yes. I have a question.
Yeah, sure. Go ahead.
Hi. So you explained about the virtual to physical mapping, which is required because the applications are running in virtual addressing mode and the data buffers are in physical addressing mode. But the kernel also does something which is more of process to process isolation. How is that handled in this case on an RDMA case? Because now everything is in the user space. So the security or buffer overlaps can happen.
There is something called a protection domain.
Yeah.
So when a process tries to, let's say, access the Infiniband adapter, first it opens a context, then it creates a protection domain. The protection domain makes sure that only the process that opened the context is able to access the memory regions associated with that context or registered with that context. So that makes sure that a separate process is not able to, let's say, read or write into this process address space without this process allowing it. Okay. Of course, we cannot, let's say, account for user error. That's a separate issue. But fundamentally, this will take care of somebody else trying to access your memory without your consent. Again, note that Infiniband was not built with security in mind. So if you have a packet sniffer on the network, then potentially you can find out the R key and access somebody else's memory. But then again, there are encryption solutions available in the network adapter to address those concerns.
Sure.
Yeah. So on the Slack, there was a question, the Infiniband atomicity guarantee. So Infiniband guarantees atomicity if multiple of such requests come from the network side. Okay. But if some requests are coming from network and some coming from the within the node, it doesn't guarantee. You need to come up with more advanced solutions. Okay.
Any other questions?
Just a follow up on the previous, which you said on the protection domain. So I have a little background on the RDMA, so maybe it's a novice question, but it seems that everything which was done in kernel or the major pieces which was done in kernel are ported to an HCA in the hardware.
Right.
That's how the RDMA is implemented. But still, there can be a rogue hardware or a application, RDMA application or a library, which can actually spoof the system into thinking that it's a uncompromised domain. For example, a CPU server can post from a hacker can actually post in or a spoof or a post incorrect domains.
So again, in the interest of time, let me try to jump to a conclusion. So I can ping you a paper. There are 9 different ways in which this can be done. Okay. There is not one. There are multiple ways in which this can be done. As I mentioned, Infiniband, when it was thought up, security was not the top of the list in terms of priority. It was performance. So there are holes. And even now, Infiniband runs in an environment where security is guaranteed through other mechanisms, not, let's say, Infiniband does not run in the wide open internet where anybody can do anything. So in a sense, that's how IB handles security. There are, as I said, not one, there are 9 different ways in which this can be done. I can ping you a paper where that was studied, and some let's say solutions to ameliorate that was proposed, but still it is not bulletproof. So again, the idea is that InfiniBand is for performance, and the thought process that my server is in a machine room somewhere, and there is somebody else making sure that only good actors get on the system. So if you have a rogue user, you are asking for trouble, basically, if you have InfiniBand.
Okay, thank you. The premise is that it's a secured environment already.
Yes.
Okay, thank you.
And again, there is research going on there. There are solutions available out there, but it is not on the top of anybody's priority list because there are other ways to ensure security. Thanks. So thank you for the question. I appreciate that. Keep them coming. That helps us stay awake and helps you stay awake as well. Thank you, Pecan. Thank you, Rohit. So let's now go ahead with the hardware protocol of offload. As Pecan said, a lot of the solutions have been offloaded to the hardware. So we look at several of the transport network link layers that have been offloaded and see at a very high level what solutions are there. We'll start off with the network and link layer. So in network and link layer, we'll cover buffering and flow control. How do you implement differentiated quality of service using virtual lanes and service levels, switching and IB multicast, as well as InfiniBand's wide area network capability. InfiniBand provides 3 levels of communication throttling or controlling mechanisms. So there is a link level flow control, then there is a message level flow control, and a congestion control. So each one happens at different levels and their goals are different. Now, if you look at the link level flow control, it has no relation to the actual number of messages that have been posted, but only the total amount of data being sent. So the link level flow control only sees if, hey, the sender is trying to send X amount of bytes. Does the receiver have enough data to receive all those X amount of bytes? That's what the link level flow control tells you. It does not care if this X number of bytes have been split into Y number of messages on the sender and the receiver side. That is handled by the message level flow control. Okay. So that is what the link level flow control is. And IB provides an absolute credit-based flow control. And the receiver guarantees that I have enough amount of data posted to receive X amount of bytes. And this is communicated to the sender in a piggybacked fashion. And through occasional credit updates by the receiver. Now let's go on to differentiated quality of service. There are 3 concepts that InfiniBand uses to implement differentiated quality of service. One is called a virtual lane, which is a physical concept. The other is called a service level. Then you have what is called as a service level to virtual lane mapping. And you also have partitions. Now, what is this virtual lane? If you look at your physical wire, there are a lot of, let's say, there is a channel adapter which is leading to the physical wire. And if you look at the channel adapter, it has a certain number of buffers which are given to store the packets coming from the CPU. Now, this buffer pool has been split up into multiple individual chunks, and this is called a per virtual lane buffer pool. Now, depending on your let's say vendor, you could have different number of pools. It could be like anywhere between 2 to 15 a number of virtual lanes. Virtual lane 0 is the default data virtual lane. Virtual lane 15 is the default virtual lane used for administrative and control packets. So the Subnet Manager entity that Dr. Panda mentioned earlier uses virtual lane 15 for communication. There is a separate thing called a service level. Now, a service level is exactly similar to like a service level that you would enter into an agreement with a vendor. So it basically tells you, I want high priority or low priority service. There is a table that maps the service level to the virtual lane. Now, the network administrator can say that I am configuring 3 virtual lanes, a low priority, a medium priority, and a high priority. And then he or she can configure the SL to VL mapping table to say that SLX maps to the low priority, SLY maps to the medium priority, and SLZ maps to the high priority virtual lane. Now, the user would be asked to say tag all of their packets with service level X, Y, or Z, depending on their service level agreement with the vendor. So this would ensure that on this particular network, the service level to virtual line mapping would be honored, and the packets which are marked with a higher service level gets processed before the packets that are marked with a lower service level. So through this, one can have differentiated quality of service and also make sure that there is things like head of line blocking can be avoided. So having mentioned that, let's go on to the next concept, which is the layer 2 routing, or let's say what we call as switching. On the Ethernet world, we have MAC addresses to do switching. On the IB world, we have what is called as local identifiers or LIDs to perform switching. When a packet comes in, the switches look up which port to forward a packet to based on its destination local identifier. And this information would be maintained at the switch. And this is populated by the Subnet Manager. And we look at an animation in a few to see how this happens. So this is basically how unicast packets are handled. Now for multicast packets, there is a separate lookup table called multicast group lookup table. And that allows the packets to be replicated through appropriate output ports. Now, if you take a look at the switch, the basic unit of switching in Infiniband is basically a crossbar. And depending on the generation of the Infiniband device, it could be like a 24, 36, or 48 port crossbar. Now, this crossbar provides the all-to-all connectivity, which means that there will not be any sort of congestion or contention inside that crossbar. But creating a large network with such crossbar units is very expensive. So typically what people end up doing is to create what is called as non-blocking switches with different crossbar sub-elements. Now, what a non-blocking switch guarantees you is that for any random node pair selection, there exists a switch configuration such that the communication is non-blocking. But if the pattern changes, there could be contention that happens in the network. So this is one important distinction between a crossbar and a non-blocking switch. And typically, all large deployments would be non-blocking in nature. They could have different topologies. Like it could be like a multidimensional torus or a hypercube or like a fat tree or like a fully or a partially subscribed fat tree. So all of these would be non-blocking in nature, but not a crossbar. Now let us see how exactly switching would happen in this sample IB network. So here you have different leaf switches and different spine switches. And we have two nodes, P1 and P2, with two processes, let's say P1 and P2, trying to communicate with each other. For the sake of this example, let's assume that P2 has been assigned two local identifiers. Okay, it could be through multiple mechanisms. It could have two network adapters, or it could have what is called as LMC, which is subnet masking, equivalent of subnet masking on the Ethernet side, and have multiple LIDs. So what P1 would do is to send a packet with a particular destination LID. So when that happens, the first switch will try to look up the destination LID and forward the packet appropriately. So here we know that for destination LID 2, the output port is 1. So it would go out of this uplink to this spine block, come down to this downlink, and then finally head to P2. Now, suppose if for some reason this spine switch is down, or if this link is congested, the availability of a second destination LID allows P1 to take a different path through the network to reach P2. So this is one benefit of having multiple destination LIDs assigned to one end node. So you have the ability to multipath through the network. And this has a lot of benefits in terms of making high availability as well as network like congestion aware algorithms. So, and all of this work is done by the Subnet Manager, and it ensures that different like paths are given to different routing algorithms. So before I go to the next slide, maybe we can take a short break here.
Yeah, so Hari, what I was thinking is let's introduce bring the hands-on exercise, the login things and all,
Sure.
and let's tell the people so that they can get the accounts ready, and we'll take a 15 minutes break.
Sure thing. So let me try to bring up the slide. So I hope you can see the slide. So you will be logging on to a remote cluster to perform the hands-on experiment. We have set up a lot of different usernames and passwords for you. So please click on this link. It will take you to an Excel sheet like this. So in this Excel sheet, we have given a lot of different usernames and passwords. So we would request that you go to that particular website and try to claim one of these usernames and passwords by putting your name against this. So this is the link, and please claim that here. And this details is available on slide number 144. Okay.
And Hari, if some of them were there in the morning session, their accounts still should work, right? They don't need to claim any new account.
No, they don't need. Well, it'll be good if you can claim a new one.
Okay. Okay.
Because
there could be conflicts. There could be conflicts.
There could be conflicts. So we would request that you like claim your accounts again. Don't rely on what was done in the morning, because like there could be people who did not attend the morning as well.
Yeah.
So please log in. And remember that whatever username you claimed from that Excel sheet is what you have to use here. It should not always be RI2TUT01. So whatever username you claim from there should be the one that is used here. The examples are located in a subdirectory called tutorial IB here. And there are several scripts. All you have to do is to like sbatch the script. So there are lots of detailed instructions that you have here. So this is what you will have to do. And if you look at this readme.x, all this information will be available to you. Remember that you are using a shared HPC cluster, which means that you have a job scheduler. So once you do the, once you submit your script, there may be some delay because others are also using this cluster. So please wait for some time for the output to show up. If you have any issues in logging in or using this cluster, please let us know, and we can definitely help you out with that.
Yeah. And let's take a 15 minutes break. We'll join back again 2:45 PST or 5:45 EST. Okay. We are posting that in the Slacks and chat also.
Alrighty then. Any questions, guys? Okay, if not, we'll see you in another 15 minutes.
Harry, I have a question. In all the way in the beginning slides, you had always like in a subnodes, they were like switches, and then on the boundaries, you had routers, but you never pointed to bridges. So that's what I recall from my networking a long time ago. I was wondering how the differences between in your picture between switches, bridges.
So bridges, in essence, so there are some use cases where we do use bridges. So when you want to go from one sort of network to another sort of network. So let's say if you want to go from IB to Ethernet or like fiber channel to something like that. So in those cases, you use bridges. But if your network is homogeneous in nature, then typically what you have is switches and routers. But yes, bridges are also there. We did not show it in that particular example, but yes, you are right. You can have bridges as well, especially when you want to do translation between two different kinds of networks.
Okay, so pretty much they are very similar, except there are multiple, there are different protocols.
Yeah, typically like one side will be talking Greek and the other side may be talking Latin. So you have a bridge to make sure that you are able to convert it to the appropriate, let's say, language, and so that the other side can understand it.
Yes, that's right. Thank you very much.
Sure.
Hari, quick two questions if you have time.
Sure.
In Ethernet, we have something called store and forward, and that's the reason for that is you need to have packet buffering because the CRC is checked at the end.
Mhm.
How do we ensure the packet is not compromised or integrity is maintained in IB?
So as in somebody didn't intercept your packet in the network in the middle, mess with it, and then
No,
send it to you.
no, not even intercept. It's because if you have kind of non-blocking, or if you have multiple feed through on the switches, there can be collisions and packet corruptions as well. And so to avoid
Honestly, I
that,
have never seen that happen. So I've been using IB networks for like 15 years. I have never once seen a packet getting corrupted on the network.
okay. So okay. Probably a second question on a different note is, in Ethernet we have all these like you mentioned about the different LIDs being assigned to one of the systems in your example,
Yes.
LID2 and LID4, so that you have
Yes.
multiple paths to reach that system P1.
Right.
Right. Effectively in networking you have similar approaches, but that is at a higher level, network level, where you find out through a
ECMP.
spanning tree or something the loops are not there, and then you find multiple routes to.
Basically, you're talking about ECMP, right?
Yes.
Equal cost multipath.
Yes, exactly. So my question is, there it is taken care by a specific protocol layer which ensures there are no loops, there are proper paths, and it's computed, and then you are assigned.
Correct.
How do you assign two LIDs in a similar way in IB? Does it be an administrator, or is it an algorithm sitting on the host which runs through and finds out?
It is a subnet manager, so it is an algorithm which does that. So, there is an entity called the subnet manager. There are different implementations of the subnet manager. A popular implementation is called OpenSM. OpenSM has a configuration file using which you will tell the subnet manager how you need to configure the cluster. How many LIDs do I want to assign an endpoint? Do I want to assign like different, how many virtual lanes do I want to create? What is the weight for each virtual lane? What is the mapping between the service level to the virtual lane? Things like that. So once you have set it, then the subnet manager will go ahead and make sure that those policies are implemented throughout the network.
Okay, and the subnet manager algorithm, it is part of the Infiniband specification itself. The implementation.
So there are two things. The Infiniband specification does not mandate that the subnet manager algorithm should be like this. The Infiniband specification, the only thing it mandates is that if you want things to go from A to B, this has to be here. The implementation is separate. It is part of what is called as the Open Fabrics Enterprise Distribution, OFED, which we'll talk about like a bit later in the slides. So the implementation of the subnet manager, all the different routing algorithms like upstar, downstar, shift, all of these things are not mandated in the standard. That is in the implementation.
Okay. Okay. Now I'm getting the picture. Thank you. Thank you.
Sure. So like there's a difference between the standard and the implementation. The standard just says that, okay, let's say, what is an LID? How should the lookup happen? What is the width? What is the packet format? So that is what the standard mandates. How you implement that is up to your, let's say, it's implementation specific. So the standard does not mandate.
But different vendors need to come up to a common kind of a standardized way of implementing so that they can interoperate. Like for example, HCA from NVIDIA should interoperate with HCA from Intel, right?
Theory and practice differ widely.
Oh, okay. Okay.
So, okay, that's more of a non-technical question. Probably I would ask that question to your Intel or NVIDIA marketing rep to see if Intel HCS will interoperate with NVIDIA HCS.
Oh, okay. So
theoretically, they should, if they adhere to the Infiniband standard. Practically, we have seen a lot of gotchas when you try to mix and match HCS and switches.
Okay, makes sense. Yeah, that's what my concern was. Like to interoperate, you need to have some kind of standard or
yes, there is a standard. There is definitely a standard. Theoretically, they should interoperate. So the InfiniBand ecosystem is not as diverse as the Ethernet ecosystem, where you have like a huge like interop festivals where vendors make sure that Cisco works with Juniper, which works with Dell, so on and so forth. So theoretically, yes, there is a standard. Theoretically, they should interoperate. Practically, we have seen issues.
Okay, thanks a lot for the clarifying. Thank you. See you after the break. Thank you.
Yeah, sure. Thanks for the questions. I appreciate it.
Yeah, so we have 5 more minutes. Sorry, if you want to take a break, short break, take it.
Sure.
Okay. So I think welcome back. So I hope all of you had a nice break with some cup of coffee or tea. Let's get started. So Hari, you can continue. If there are any quick questions, we'll be happy to answer now also.
And keep them coming. It's good to have questions.
Yeah.
So let's go forward to an example of how multicast works. So there are two cases, there are two possible deployment scenarios on InfiniBand networks where you have Subnet Manager either running on a compute node or on the switch. For larger networks, we typically see the Subnet Manager running on a compute node. So what happens is something like this. Let's say if a process wants to join a multicast group, then the process would send a note to the Subnet Manager saying that, hey, I want to join this multicast group or create a multicast group. The Subnet Manager would then create the multicast group and configure the multicast tables in the appropriate switches with the appropriate entries. Let's say in the future, if other processes want to join the same multicast group, the Subnet Manager would then make appropriate changes to the forwarding entries on the switch to make sure that the actual multicast functionality would work appropriately. So in this case, these two entries would be added to switches to make sure that different nodes get the actual multicast packets. So this is what is about IB multicast. So as we mentioned, when Infiniband came out, they were meant as a system area network. It was not meant to go beyond like a server room. But then as more and more IB deployments came up, people wanted to see if they could combine all of these IB deployments. They could be either inside a campus, inside a building, or across the country, across the world into, let's say, one large cluster kind of a scenario. So this is where Infiniband's wide area network capability began gaining increasing attention. So there are a lot of different products by different organizations like NVIDIA, Mellanox has some switches and routers. Obsidian Research Corporation have what is called as range extenders. Bay Microsystems have their own solutions. And similarly, recently NVIDIA/Mellanox had an announcement of their quantum long reach product. And there is an organization in Singapore called A-Star Computational Resource Center who are trying to build an InfiniBand network around the world. So there are different kind of organizations out there trying to build wide area IB connectivity. So that is what we will talk about the network and link layer. So now we go up one level to the transport layer, and we'll see what different types of capabilities IB offers at the transport layer. So if you look at it, IB has different kind of transport protocols. So you have what is called as the reliable connection, which is equivalent to TCP/IP on the Ethernet world, and unreliable datagram, which is equivalent to UDP. Now, each of these transport protocols have different cost performance trade-offs. Now, while reliable connection is feature rich, it has a lot of cost in terms of number of QPs required to establish all-to-all connectivity. So this may not be the best for scalability while it is awesome for performance. However, UD on the other hand is very good in terms of scalability, but does not have a lot of high-end capabilities like RDMA or atomics. But so what vendors try to do was to create like protocols which provide the best of both worlds. So this is where protocols like the extended reliable connection or dynamic connected or DC come in, which gives the scalability of UD while giving you the rich set of features that RC provides. So these are what is called as the connectionless protocols, and this is what different vendors are projecting as what is required to go to the exascale systems. Now, some of the transport layer capabilities are as follows. Again, this is not an extensive or a full or comprehensive list. So we have data segmentation, transaction ordering, message level flow control, and static rate control and auto negotiation. So first, let's see what message level flow control is. Okay. Now, inside IB, what you can do is that suppose you have a 1 gig data to transfer. You can just give that as one message, one wookie to the IB network, which would then take care of segmentation, reassembly, make sure that the packet is sent in order, stuff like that, to the remote side. Now, depending on the transport protocol, you can either have a strong transaction ordering or no ordering at all. So if it is RC, which is reliable connect, the equivalent of TCP/IP, the network adapter guarantees the order in which the cookies are posted on the sender side is the same order in which the cookies are received or made visible to the application on the receiver side. So if you are using one queue pair and if you have static routing, then all cookies posted on the same queue pair will take the same path over the network. All packets received by the receiver are in the same order as made available or made visible to the end application, and they are completed in the order in which they are posted. Now, we also have what is called as message level flow control at the application level, which is also called end-to-end flow control. So this is again separate from the link level flow control. And this ensures that the number of messages, high-level messages, are equal on the sender and the receiver side. So let's say if the receiver posted 10 cookies, but if the sender wants to send 15 cookies, then now you have a mismatch at the transport level flow control or the message level flow control, because the last 5 cookies will not have corresponding send cookies, will not have corresponding receive cookies on the receiver side. So if you are using a reliable transport protocol like RC or DC, now the sender's packet will get throttled. The receiver will send back a message saying that, hey, I am not ready. Receiver not ready. So then the sender will wait. However, if you are using an unreliable transport protocol like UD, the sender will just send the packet. The receiver on receiving the packet will figure out that, hey, there is no buffer for me to place this packet at, and the packet would get dropped. So this is what happens with the message level flow control depending on your transport protocol. Now, Ib also allows the link rates to be statically changed. So as Dr. Banda mentioned earlier, we have different number of twisted pairs of wires inside a cable. So Ib allows you to change the rate in multiples of these like wire speeds. And unfortunately, unlike Ethernet, you cannot set the rate to something like 3.16 Gbps or 5.89 Gbps or anything that you want to. So it goes in like fixed chunks. Ib also has capability for auto negotiation. So auto negotiation is the feature where if you connect, let's say, an SDR or single data rate adapter to a HDR or a high data rate switch, they still like talk to each other, figure out what is the lowest acceptable rate, and they will be able to communicate with each other. So this capability also exists in Infiniband, which allows you to mix and match different generations of network adapters for functionality. Performance is a completely different question, but they will work together. Okay. Now let's go on to the next topic of subnet management and associated services. So there are different concepts in Ib subnet management. You have subnet agent, subnet manager, messaging schemes, and messages. So there will be one or let's say a few managers for high availability purposes, and every single network entity will have what is called as a subnet agent running on it, whose responsibility is to implement the orders of the subnet managers sent through messaging schemes called managing datagrams. So the first thing that would happen is that the subnet manager would come up. It would broadcast a message to the network saying that, hey, I am here. All the subnet agents would sign in, so that the subnet manager figures out that, okay, these are all the different switches and the compute nodes, and it would compute the routing and switching algorithms, make sure that all the forwarding tables have been populated, and once it has been done, it will set all the links to the active state. At this point in time, the network is ready for communication. After this is done, the subnet manager will periodically sweep the network for any changes, or the subnet agents could send trap messages to the subnet manager to inform them of any changes. Now, if through one of these mechanisms, the subnet manager realizes that a node or a switch has gone down, then depending on the complexity or the impact of the change, the subnet manager will reconfigure the network and make sure that the appropriate link is marked as inactive, and the routing and switching tables are modified. So that is about subnet management and other related services. We'll briefly talk about like other architectural protocols. So here we are talking about what is called as IP over IB and SDP. So initially, InfiniBand and Ethernet, they wouldn't talk to each other. Let's say you had verbs and you had, let's say, TCP/IP going on the other side. But that is not great for business. What if you want, you have a sockets application, but they want to run over an IB network? So what do you do then? So that is where people came up with this thing called IP over IB, where you have a traditional sockets application with sockets API going over the IB through the kernel and TCP/IP provider. But when you go through the kernel, the performance sucks. What can we do to get better performance? So that is where the sockets direct protocol came in. So here the API is still the sockets, but instead of going through the kernel, we try to bypass the kernel for large message transfers, and thereby we get very good performance in the large message range. However, because you still have to go from the user space to the kernel space, because of the sockets API, you still don't get very good latency in the small message range. So in order to address this limitation, people came up with what is called as RSockets. So RSockets is kind of an LD preload library, which uses the Rdma CM method and verbs to bypass the kernel and thereby give you good latency as well as bandwidth. Now, with the advent of these two protocols, now this is how your protocol slide look like. So you have TCP/IP on one end, you have IP over IB and RSockets and SDP in the middle, and you have RDMA on the other side. And as we go on, we'll populate the other holes in this slide as well. Now, with this, we'll go into the high-speed Ethernet family, and I'll hand over to Dr. Panda for a bit. While we switch over, is there any question?
Yeah, so in probably a little bit off the track here again, in the sense that IP over IB, who does the packetization? That means chopping the bigger data into packet size payloads in that case.
The driver will do it, and the driver can driver can be implemented either in the software or on the hardware. So depending on the adapter being used, you can have what is called as a TCP offload engine or TOE. So if the adapter has this capability, then it will be done in hardware. So some adapters have what is called a segmentation offload and other such capabilities. So depending on the hardware, it would either be done in the driver or in the HCA hardware.
Okay.
Okay. So now let me, so you can see my screen, I think.
Yes.
Okay. So we learned some concise description of the Infiniband and the related protocols. So now let's take a look at a little bit about the other technologies. We'll start with high-speed Ethernet family. So there we'll take a look at the IWARP, which is called Internet Wide Rdma Protocol, and then some alternate vendor-specific protocol stack. So here again, we'll try to, instead of repeating everything, we'll take a look at the architecture components and try to take a look at the differences between what Infiniband does and then what IWARP does. And IWARP, I don't know how many of you heard of this term. This is like a, there is a one single product out there now called the Chelsio. If you would have heard of Chelsio adapters, they support this IWARP. Earlier, there used to be another company called NetEffect, and that was acquired by Intel. So if you take a look at the broad differences between, let's say, the Infiniband and this IWARP, many of these are similar, like the hardware acceleration, RDMA supported. There are some differences, and we'll pick only two of these, and that will illustrate the differences. So a little bit of history about IWARP. I mean, here I'm giving a lot of history, but that is important because many times if you don't know the entire thing, you don't know why suddenly this technology came into the market. Okay. So the IWARP has almost started as Infiniband came. As you know, the Infiniband, when it came, it has the RDMA or the remote DMA, and it started giving good performance. So then people started, the Ethernet community started asking questions that can we take RDMA to Ethernet? Okay. It took some time for people to understand that RDMA is a mechanism. I hope all of you would have understood it also, RDMA can be used for any network. If you redesign your underlying adapter and switches, you can have RDMA. And that's what all the modern high performance networking adapters and protocols are doing. But this was the very early phase when IWARP, if you think of like this TCP IP stack, people wanted to see, okay, how I can bring RDMA on top of it. So in order to do this, they introduced these 3 modules. One is called RDMA Protocol, RDMA Remote Direct Data Placement, and this is most important. It's called marker PDU aligned. So let me go into more details of these 3 modules. So the idea here is that think of like the RDMA, let's say if you are sending a large amount of data, it has actually comes in a big packet. Infiniband has its like as Hari indicated, some message level packetization and all, but the data arrives whether it is in or out of order. But if the data is out of order, think of like I send a 1 gigabyte data from the sender side, and especially in the Ethernet, where there is a lot of flexibility for switches to split the data, some switches to combine the data, all those functionalities are there. You cannot guarantee that the data has been received at the receiver in the same order. If the data is out of order, of course, it will lead to all kinds of data validation issues and corruption. So this has issues both from the application perspective as well as protocol stacks perspective. So the application perspective, let's say receiver is waiting for the data to come. Let's say the second half of the message first got arrived. It doesn't mean that the first half of the message has arrived. Okay. Whereas Infiniband actually tries to guarantee it, and especially Mellanox Infiniband tries to guarantee that. Similarly, if one message has been placed, it doesn't mean that the previous message has been placed. So in order to solve this problem, this protocol stack also has the same issue. Like the receiver network stack has to understand each frame of the data. So in order to handle this, they introduced this Mpa protocol. So if I go back to the previous slide, so this is where the marker PDU aligned was introduced. The concept is very simple. If you think of like an Ethernet, always like Ethernet frames are 1024 bytes, right? 1 kilobytes. That is the normal one. There are jumbo frames and all. So what they try to do, before you inject the message at the sender side, in every 512 bytes, you put a marker. That's how the name comes, marker PDU aligned. So that means if I have a large data, I start from here. After 512 bytes, I put a marker 1. Another 512 bytes, I put marker 2. So like this. So I need to reconstruct the packet before pushing it into the network. That's what happens. If it's an application library, it goes through some of these interface, but then you go through this MPA and then you push it through the TCP IP. Okay. So what it means that if you put these markers, and since the packets are like frames are 1024 bytes, when the receiver receives it, doesn't matter whether some packets got split or something got combined, at least you will have one marker when you receive. If you receive only a chunk, you will see that at least 1 or 2 markers will be there, and that will quickly tell you where the relative location of that packet is. Okay. So even though I sent it in some order, in some switches, it got split. One split got received first. It might be the 20th marker, the packet with the 20th marker arrived first. So in the receiver buffer, I'll put it at the 20th place. Then I get 5th, then I get 1st. So once I get all the packets, then I give it to the receiver. So then I can provide the semantics of the RDMA. So that's what actually is the IWARP architecture in a nutshell. And this has some overhead because you are trying to carry out these. So in the Chelsea adapter, if you run it in their basic network bus versus like IWARP, you will see some kind of performance difference. Okay, but that actually allowed the Ethernet family to come with the IWARP. So that means any other RDMA protocols or upper layer protocols which are utilizing verbs should be able to run. And we'll talk about that a little bit more details. So the 2 other features where things differ between Infiniband and Ethernet, again, there are multiple of them. I'm just picking 2 because of the lack of time. So this is a dynamic and fine-grained rate control. Okay. So typically, if you see like an Ethernet standard is a part of the Ethernet standard, not IWARP, dynamic bandwidth allocation. So consider, let's say I have a 10 gigabits network and I want to allocate only 5 gigabits per second. So typically what happens, you introduce stalls on the sender side, you introduce stalls for every packet. And these kind of mechanisms are very much needed for high latency, high bandwidth network. Okay. I don't know how many of you are familiar with this. It is not low latency, high bandwidth. It is high latency, high bandwidth. Okay. And these are typically intercontinental links. Okay. Let's say we are trying to provide connection between Amsterdam to New York or Tokyo to Seattle. So there what happens if you totally depend on receiver being not ready, and then a lot of messages can be on the flight. And if some packets get dropped, it creates a lot of other packets to be dropped. So that's why you need sender side control. So that's what exactly is achievable in the IWARP or Ethernet, but not on Infiniband. Okay, Infiniband, if you remember, we discussed, you need to have appropriate buffers. Otherwise, the message gets dropped. There will be some retransmission to take care of it. The second one is prioritization and fixed bandwidth QoS. Okay, so this is related to the service levels. We talked about Infiniband. IWARP also provides very similar to service levels. There are priority classes, management traffic, regular traffic. But IWARP or Ethernet, you can actually request for specific bandwidth. Okay, so there is a protocol, if some of you would have studied, called RSVP. It is just like our normal invites. You invite, you say, okay, you give an RSVP. So same thing happens in the Ethernet world. If there is a sender here and receiver here going through a lot of switches and links, I can, before I send the data, I can request for a service. So might be it is a 10 gigabits per second, but if my data transfer only requires 3.62 gigabits per second, I can request it. Okay, so there are some protocols. It will go through all the switches, links, try to dedicate that. Some packets, reply acknowledgements will come before you start transferring. But those kind of things are not available in the Infiniband. Okay, so that's why whenever people talk about multimedia and all those things, those are very hard to do with Infiniband. Okay, multimedia, streaming, dynamic bandwidth allocation. So that is the big difference between Infiniband and IWARP. But this IWARP, because of the feature I indicated, Rdma, what actually worked is if you see the IWARP, so from the Ethernet side, everybody was going through sockets, and we introduced these R sockets and STP in some of the earlier slides. STP was using Rdma. It gives reasonable performance. But here, IWARP with Ethernet switch, IWARP adapter was able to exactly match with Infiniband, like the same user space protocols, but instead of Rdma, it was like a TCP IP with some Rdma emulation you can do. And the more important thing that both of these were linked to the verbs. Okay, so that means if any application or middleware has been rewritten for Infiniband, now it will directly run on the IWARP, and that was actually the biggest strength. So in fact, in the few slides, we'll talk about open fabrics, software stack. Some of you might have heard it or used it. Prior to that, if you go back to 2000, 2001, it was called Open Infiniband, Open IB, because the DOE labs started with only Infiniband because there was no other technology coming. But then once IWARP and NetEffect, or say Chelsea and NetEffect, tried to join the consortium, they changed the name to Open Fabrics. That is because of this. Because now, if let's say, for example, an Mpi library is rewritten with verbs, now it can run with Infiniband, it can run with NetEffect, or it can run with Chelsea. Okay, so that was the big advantage in the community to bring the Rdma kind of design into the high performance networking world. So as you can see, gradually we are filling up this column. There is one more left, so let's try to take a look. But after that, we'll also expand it. So these are the kind of the key slides, key takeaways you can from this tutorial. But before I jump into that last column, I also want to touch base, especially in the Ethernet world, there are a lot of vendor specific stacks. Okay, so I'll talk about a little bit two of these. One is the Miricom and then SolarFlare. So Miricom I introduced earlier, like Miricom was a proprietary network, Mirinet, that was the very first cluster interconnected came. Of course, once Infiniband came, after Mirinet, there was a network called Quadrix came. But then once Infiniband came, those gradually died down. But Miricom looked at a little bit different aspect, just like the kernel bypass layer I talked about for reliable communication. They introduced a software stack called datagram bypass layer, or DBL. Okay, So here the idea, again, this is not an open source stack. It is a stack is covered by NDA. Similar stacks have been designed by Emulex, but the primary target is financial market applications, not the traditional HPC, but financial market with a focus towards high performance. Now, if you take a look at the high performance, the financial market, typically, the stocks are changing, the clients are connected to that server, the client should be getting periodic updates, but it doesn't guarantee, it doesn't mean that each and every client should receive each and every tick of the stocks. If something gets dropped, those are okay. Quickly, you will get the newer values of the stock very soon. So that's why instead of working on the RC, they try to bring this kind of the kernel bypass concepts into the UDP sockets. So here the idea was that to give high performance and low jitter, and timeliness is more important than reliability. Okay, because there's a different kind of community, and if you can, reliability is not important. If some packets get dropped, it is okay, but we should be able to deliver timeliness and high performance. So there are some of these solutions which are still used in the financial market. So then there was a company called SolarFlare. It has been acquired by Xilinx in 2019. So we talked about this OS bypass protocol, saying that, okay, you do the user level communication versus kernel level communication. The SolarFlare was one company. It came with a hybrid solution. Okay, so that means the protocol processing can happen in both kernel and user space, and the protocol state can be shared between both application and kernel. Again, it is an NDA thing, so we don't have much the details to talk about, but if you are interested, you can always talk to them, and they have been acquired by Xilinx, so you'll be seeing some solutions coming out along these directions. So those are the kind of the samples of the Ethernet, but now let's take a look at the convergence. This is what a lot of things are happening now. So this convergence, if you see, even though Infiniband has been there for many years, and especially in the beginning, there was a lot of resistance for the community to use Infiniband because somebody has to know all the new things, understand the new protocols. The system administrators have to know all these things. Even though you get the best performance, there's a lot of overhead. So this is where people ask questions saying, okay, can we have some hybrid solutions? Okay, so Mellanox started this in the beginning something called a virtual protocol interconnect. It is still available. They call it VPI. You can talk to them and get VPI adapter. So the idea was that some of the initial adapters, Mellanox had 2 ports. So the question is, can one port work as InfiniBand and another port work as Ethernet? Okay, and especially in the beginning, there was a lot of need for these. Currently also, you can deploy system. For example, let's say you have a data center. Inside communication, you can do it InfiniBand, but outside communication, you can do it Ethernet. So if you have an adapter with 2 ports, you connect one of the ports to the internal switch, another port to the outside. So then you are able to support both native InfiniBand for performance within the data center, and outside you are trying to provide the sockets. And the way they try to do, if you see the stacks, this is Ib verbs, all these things we discussed, but here directly they go through the sockets going through the TCP/IP, and they have the auto sensing of the layer 2 protocols. So you can mix and match not only data centers. Let's say you have a cluster with IB network, but you want to do management, you can do the management over Ethernet port. So those kind of solutions were provided. But then recently what happened, Mellanox wanted to sell their adapters also for Ethernet environment. So that means people wanted high performance adapters to work with Ethernet switches, okay? Because people had deployment, like let's say insurance companies, they had a lot of Ethernet deployment, but if you depend on the socket stack, that was not giving them the good performance. So then the question was, can the adapter support RDMA, but still work with Ethernet switches? Okay, so this is where Mellanox entered inside. First, they introduced this protocol called RDMA over Converged Enhanced Ethernet called ROCKY. And so now if you see the stacks, this is the pure InfiniBand stack, application, Ib verse, transport, network, InfiniBand. So here, everything remains the same, but on the adapter, it happens with Ethernet. So what they actually tried to push to the market is exactly the same adapter. Okay, only the lowest layer being different. Hardware is the same. Instead of working on the InfiniBand link layer, you can work on the Ethernet link layer. So that's how they were able to combine like a InfiniBand adapter with Ethernet switch. So that opened up a newer kind of market for the community, so that you can take advantage of all the RDMA software, MPI, file systems, Lustre, everything whichever has been converted to VERBs, you can utilize that with Ethernet. Okay. So see that this is not iWarp. iWarp went for a pure implementation of RDMA over Ethernet. Here they use the most of the Infiniband features, just changed a little bit to match with the Ethernet. So that actually Rocky V1 has been there for many years. So now there is a focus on the Rocky V2. A lot of new deployments are coming. In fact, Broadcom, their adapter actually supports Rocky V2. A lot of some cloud deployments are also taking place with Rocky V2. So here the idea is that in this middle, the network layer, instead of network, you try to do UDP/IP. Okay, so that actually opens up a lot of a typical deployment like ACLs, snooping, network monitoring tools. All these things can actually now work in a seamless manner. And these kind of environments, in a nutshell, you can think of it as Infiniband software and Ethernet hardware. Okay, think of like this in a loose manner. That means you have all these Infiniband software, whatever has been rewritten over the last 20 years, but you have Ethernet hardware, you can plug them together. And that gives actually a lot of opportunities. For example, you can buy Rocky adapter from vendor X, Ethernet from Arista. There are a lot of choices you can do. You don't have to stick to one vendor like Mellanox. Okay, so that is good for vendors as well as it is good for the customers. So that stack actually comes here, you see. So this is the Rocky. So it is exactly the same RDMA user space. Instead of Infiniband switch, you have Ethernet switch. Instead of Infiniband adapter, you have Rocky adapter. Okay, and again, they're sitting on below VERBs. So any software stack, whatever has been VERB enabled, can now run on iWarp or Rocky or Ib native in a transparent manner. So this is the one important slide, slide 83. If you want to take away anything, just remember this slide 83. All the terminologies of high performance networking protocols are here. Okay, and we'll only the OmniPath, which is not there, but that we'll add very soon. So here I think I'll hand it over to Hari. So most of the discussions we have done with Infiniband Ethernet, then gradually we'll try to quickly go over all the other network technologies and try to see what are the new things in those. The common things, RDMA and all, we'll not talk about, but the newer features with OmniPath, NVLink, EFA, all those things we'll be talking about in the next section. Any questions by anybody?
Yes. Do you have time for one question?
Yeah, sure. Yeah, we have time. Sure,
So,
go ahead.
This is more regarding the last slide which you showed, where the Rocky V2 architecture was there.
Okay.
The UDP is undeterministic protocol.
On reliable diagram. Sorry.
Yes.
Instead of the TCP being reliable, is the unreliable datagram protocol.
Yes, exactly. Yeah. So it can be out of order. You can have packets out of order. Now that is okay for if you are doing a file type communication, because effectively you have to, or even for probably RDMA, because if you have to copy a memory buffer from one address to another, you will consider it as a complete buffer, like from 000 location to 1xx000 or FFFF. And it can come in any order, and you will not access that buffer till all the buffer is full with the data. But if you are doing a block application or a transfer where sequence is critical, how do you handle that in Rocky V2? Like,
I unfortunately don't have a direct answer. Hari, do you have on the Rocky V2 how they specify that UDP/IP layer?
Maybe we can take this offline in the interest of time. So Pecan, I can follow up with you after the tutorial. Okay.
No problem.
Thanks. So going forward, we are going to briefly discuss about OmniPath, NVSwitch, NVLink, the Amazon EFA adapter, as well as Cray Slingshot and the Fujitsu Tofu. So OmniPath has taken different incarnations. It was initially PathScale, then QLogic bought it, then Intel bought it, and now it is being currently pursued by Cornelis Networks. So this is like a brief history of how OmniPath has evolved over the last several years. It has, just like Infiniband, it has different layers, like the link layer. There is a link transfer protocol, like the link layer 1.5. It has your standard link layer, your data layer. It has a more extensive support for quality of service. So unlike Infiniband, which only supports 16 virtual lanes, Omnipath supports 32 virtual lanes, 31 data and 1 for control traffic. And the credit return policy is kind of very similar. The QoS is implemented exactly in the same way. You have service level or service channel to virtual lane table, and you have like virtual lane arbitration table. And you also have the capability to partition the network into different domains, and different nodes can be part of different partitions. So this is more like the virtual VLAN concept you have on the Ethernet side. So Omnipath allows you to have different nodes and different partitions, allowing for more let's say finer grain management solutions. On the transport level, Omnipath uses what is called as performance scaled messaging, which is designed for the HPC needs. It has also support for the Open Fabrics interface, or OFI. So this is like a more general purpose interface, which was meant to kind of bridge the gap, the semantic gap between the needs of the applications and what is being exposed by the networking hardware. And it has support for the Open Fabric Alliance's verbs interface for Rdma IO capability. So at a high level, this is the solution that Intel and now Cornellus Networks has for Omnipath. So with the advent of Omnipath, like our slides kind of become full. So you have sockets, you have verbs, and you have OFI going over Omnipath at this very end. And this slide gives you a feature comparison for like various networks like IB, IVAR, Rocky V2, and Omnipath. So this you can consider like these two, this slide and this slide as your cheat sheets. If you want to have a quick reference to what is being used on your system. So recently, because of the issues in getting data to the GPUs, NVIDIA came up with newer interconnects for themselves called NVLink and NVSwitch, so that you can connect different GPUs together as well as connect GPUs directly to the CPU. So if you have a Power 9 CPU, instead of the GPU going on a PCI slot, it can actually go in on an NVLink slot. Thereby, you get significantly improved bandwidth between the CPU and the GPU. So we'll quickly go across the NVLink architecture, and depending on
Harry, I have a question, Harry. Quick your question.
Sure.
So for HPC, what do you think if, since most of the Ethernet connections are full duplex?
Sorry, can you please repeat that, Hesham?
Since most of the Ethernet connections are full duplex?
Yes, so IB is also full duplex.
Exactly. So if we eliminate the Ethernet MAC, because we don't have many stations, only full duplex, point to point, then we can run IP and run all protocols over Ethernet PHY without Ethernet MAC, which will save time and support high HPC. What do you think?
That's an interesting thought. It may work, but I'm not entirely sure. Maybe we can take this offline, Hesham.
Sure,
Is that okay?
Sure.
Thank you, but that's a very interesting thought.
Can you send me your email address? I can communicate with you later.
Sure.
I'll post it. It is there on the slides, but I'll post it.
Sure.
Thank you very much. Thank you.
Thanks. So this is how the NVLink performance has increased depending on the generation of your NVIDIA GPU. So the V100s had about 300 gigabytes per second NVLink performance. And NVLinks can be made in different configurations. Each GPU has multiple NVLink ports, like 4 or 6, depending on the type of GPUs you have. So you can have like NVLinks connected to like an NVLink enabled CPU, or like a Power 9, or like a PCI enabled CPU, like an Intel or an AMD processor. And inside a node, you can have all the NVLinks within a socket connected or across sockets connected. So this is a sample configuration for a DGX 1V server. But the problem is that because of the limited number of ports available on NVLink, you can only go so much. There is only so much connectivity that you can make. If you want to add more GPUs and have better bandwidth, then you need to have a switch. That is where you the NVIDIA folks came with what is called as the NV switch, which is a fully connected NVLink capable solution. So if you look at an NV switch, they have multiple NVLink ports, each capable of 50 gigabytes per second both directions, or 25 gigabytes per second in one direction. So if you look at one NV switch, it is again a full crossbar internally. And what typically happens is that you can connect two NVs, two such NV switches together to have intra-baseboard and inter-baseboard communication. So if you look at the communication within these GPUs, it will have full non-blocking capability, and you'll be able to go at almost 300 gigabytes per second. However, if once you go inter-baseboard, as in from one of the GPUs on this baseboard to one of the GPUs on this baseboard, you could potentially run into issues. So you have multiple links here. So depending on who's talking to whom at any given point in time, you could potentially have congestion or overlaps, contention happening in the inter-baseboard link. So each one of these is 25 gigabytes per second. Like in one direction, and there are 48 such links. So this is like a high-level overview of the NV switch topology. So with these kind of devices, you literally can have a supercomputer in a box. Okay, so if you are like a deep learning expert or somebody like that who really doesn't bother going to like an HPC center, you can have one fat computer sitting underneath your desk. It'll be noisy as hell. That's a separate question. But like you could use liquid cooling and all that jazz. So you could literally have all the compute power you'd ever need in one computer, one physical computer sitting below your desk. Okay, so imagine that you have like one computer with 16 A100s in your office. Most people would probably not need anything more than that. Okay, so these kind of interesting network topologies allow you to build extremely dense compute systems, so that let's say with a few hundred or a few thousand nodes, you could reach the top spot in the top 500 supercomputers list. Like the Selene supercomputer that NVIDIA came up with, which is called as the DGX SuperPod, is one such example. So now let's go on to like the different network adapter, the Elastic Fabric adapter from Amazon. So this has again gone over multiple generations and from different speeds, from 1 Gbps all the way to the current generation, which offers about 100 Gbps. But the latency is not as good as other high-performance interconnects. While other high-performance interconnects have a latency of around 1 to 2 microseconds, this has a latency of around 15 microseconds. But again, it has very good bandwidth, and it has a very good capability to spread the traffic all across the network, so that your network behavior is more balanced. So from Amazon's point of view, that was more important than having like something with very low latency. They want to make sure that their data center business is not affected because of pushing in HPC traffic. So that was one of their key goals. And just like Infiniband, Omnipath, and everything else, they have OS bypass. They have network-aware multipath routing, and they introduced a new queue-pair type called scalable reliable datagram. So this also supports UD, but if you look at scalable reliable datagram, it gives you the same scalability as UD with the data delivery guarantees of RC. So initially when SRD came out, it did not have support for RDMA, which means that you had to chunk up data into 8K chunks. But with the latest generation of EFA adapters and software, Amazon has enabled support for the RDMA read protocol, so that now you have support for direct RDMA operations from source to destination node. So that significantly improves the bandwidth performance of the EFA adapter compared to the initial version where they did not have support for RDMA. One of the major difference between SRD and UD is that this is reliable. which means that you don't have to take care of packet transmission at reliability reasons and things like that. So that is one of the major benefits of SRD. So it is again like a good compromise between the unreliable datagram and the reliable connection. So this is again a very scalable, very high performance protocol that Amazon has brought out. So let's quickly look at the Cray slingshot architecture.
Quick
here.
question.
Yes.
Yeah. So for reliability, you need to do packet buffering for retry buffers, right? You need to have retry buffers also. Will that not? Yeah.
Yes, we need to have it. If your application is doing reliability, then yes, the application or the middleware or communication substrate will have to have that support.
Yeah. So this increases the memory requirements on the host, like for Amazon's host.
Yes, it does. But the thing is, here the reliability is handled in the hardware, not at the software. So there is no additional memory requirement.
Okay.
So this is Cray's 8th generation scalable interconnect. Now, if you look at the top 500 systems, there are several systems, at least 4 or 5 of them in the top 100, which are using Cray's slingshot network. We will show this in some of the upcoming slides. One of the biggest benefits of Cray's interconnect is efficient condition control and uniform low tail latency. So these are a couple of things that Steve Scott had highlighted in his Exacom 19 keynote talk, where he talked about the slingshot interconnect in detail. Another big thing is that it is Ethernet compatible, which means that your network is Ethernet. So what they call this high performance Ethernet for supercomputers. Okay, so this is one other big change that slingshot brings in compared to other high performance interconnects out there, which are not like natively Ethernet compatible. So the slingshot switch is called a Rosetta switch. So it has a lot of hardware offload capabilities, as well as very nice QoS capabilities. So with a Rosetta switch, you can create very scalable, very high performance network topologies. So this, for instance, is an example of how you would create like a Dragonfly topology, which can potentially scale up to 279,000 endpoints with a network diameter of just 3 hops. So you have like different kind of topologies here. So you could have like a Dragonfly between all groups, and within a group you can have let's say like a fat tree or a torus, any such topology within like a group. So slingshot has like a highly tunable quality of service guarantees, which allows you to use multiple traffic classes to perform performance segregation, performance isolation, and give you very good network tail latency. And it allows you to make sure that if you have multiple traffic classes going on the network at the same time, one does not affect each other. So it gives you very good traffic isolation and thereby avoid head of line blocking. So Rohit had a question. So slingshot, it goes natively over Ethernet. So beyond that, there isn't a lot of details available out there unless you have like an NDA with Cray/HPE. So it is native Ethernet, and their high-level protocol right now is verbs, but in the future it would become OFI. So if you look at the Perlmutter system, they have like a NVIDIA Mellanox ConnectX-5 interconnect connected to the slingshot network. In the future, that would get replaced by probably a different interconnect once the slingshot network adapters also come out. So right now you can kind of sort of consider it as Rocky. So going forward, we'll talk quickly about the Fujitsu Tofu interconnect. So the Tofu interconnect is a 6-dimensional mesh or torus network topology. It has 6 coordinate axes. So it has like 2 tori built on top of each other. So you have a small tori, which is this one. So you have the A, B, and C dimensions there. And then you have a larger tori, where you have the X, Y, and Z dimensions. So this fusion of 2 different tori is where they get the name Tofu. So Tofu stands for torus fusion. So you have 2 different tori networks built on top of, like, overlaid on top of each other. So just like the previous slingshot, where you had like 2 different network topologies, where the higher one can be like a dragonfly and the lower one can be like fat tree. Here you have like 2 different torus interconnects, which are kind of built in to form the larger HPC system. So you have multiple different RDMA engines to inject data into the network. And each engine is responsible for injecting data either in the XYZ dimension or in the ABC dimension. So you have some sort of resource provisioning there between like the 2 different dimensions. And they have a lot of solutions available here to make sure that the TOFU network interfaces are used in a round-robin fashion to avoid collision in the network. So depending on the generation of TOFU, like TOFU 1 versus TOFU 2 versus TOFU D, the data transfer rate, the number of signals per link, as well as the overall injection bandwidth differs. So while TOFU D has lesser link bandwidth, it has more number of network interfaces per node, and like a higher data rate. So overall, you get like good injection bandwidth, still lower than TOFU 2, but it is capable of injecting data in multiple dimensions, which leads to better overall application performance. And TOFU also has support for what is called as dynamic packet slicing. So you can make sure that your packets gets sliced, and this allows for better performance in the network. And you can also have like a different way to have error feedback into the network. So finally, TOFU also have solution to have collective offload in the network. So this kind of shows the resources the TOFU network has for offloading the barrier collective. So it has like significant support there, and this benefits in your overall communication performance. So with this, let me hand over to Dr. Panda. In the meantime, are there any questions?
Which one of those supports cut-through switching?
So I think most of these do support cut-through switching.
Okay, so you can see my screen. I'm just hello.
Yes, I can see your
screen. Yeah. Okay. So thanks, Hari. So we are coming to the almost the last 30 minutes, 24 minutes. So what I want to cover is like we have learned all these different architectures and all. Just let's take a look at some of the hardware software products, installations, trends, market trends, and some performance numbers. And then we'll go into the hands-on exercise. And what we'll try to do, since we are running a little bit late and the time is very short, I'll cover all these things and conclude officially, but then we'll be there for several of you who have signed up for a hands-on exercise. We may take a little bit more time, and then we'll finish that. So especially Infiniband, and I'll focus in this section mostly Infiniband, Ethernet, and Omnipath. These are the commodity kind of the products. In the beginning, 20 years back, when Infiniband started, there were a lot of vendors, and there have been a lot of acquisition kind of things. Acquired by Voltaire was acquired by Mellanox, and QLogic was acquired by Intel. So like this, these days there are a lot of products out there. Sometimes even Oracle entered also market with the IB products, and then they didn't continue. So especially we talked about all these different IO interfaces and all. So you, in order to design a system, you need to look for your servers, your PCI interface, and then the adapters. So they need to, and the switches. So they need to work together. Some of the adapters in the very old days, Infiniband adapter, we talked about all those RC, Q pairs and all, you needed some memory. And that's why the adapter had memory. But over the years, once the PCI Express came, the memory, you don't need any memory in the adapter now. You can directly access the physical memory because PCI Express is faster. So that has led to this idea of mem-free adapter. And the goal is that you can have landed on motherboard designs. In fact, some of the, if you go to Tyan, they have some Supermicro Tyan motherboards with InfiniBand adapter already there. Just like we get our laptop servers with Ethernet ports, so you get those with InfiniBand. So you don't need to buy separate adapter. But they typically lag a little bit compared to the very leading adapters. But over the years, they come up with the integration. And then, of course, you get a lot of different speeds. And then all these Mellanox latest ConnectX adapters, gradually, they are providing a more and more offloading capability. I talked about the SARP. I talked about the Bluefield DPU. So in fact, in our analogy of executive secretary, they are really making the secretaries really, really powerful with a lot of capability. You can think of it's like a compared to a high school degree holder secretary. They are trying to go for a bachelor's or a master's level secretaries. In future, they may go into like a PhD level secretary also. So then the switches are available, again, all different things. I'll not repeat because of the time. Over the years, things have evolved. But these days, you typically get very large switches, the top of the rack switches, also the director level switches. So using a few hops, you should be able to really go into very large scale systems. And then there was a question earlier, like these bridges. So here you can think of like the routers and gateways. There are solutions available from InfiniBand to fiber channel, InfiniBand to IP. Depending on your requirements, you can also use that. Then Ethernet side, especially the traditional Ethernet as well as this Rocky V1 and V2. So that is a very wide market. So you get all these adapters from all these different vendors we have listed here, as well as all the switches. So you should be able to see you have a lot of choice from the end user's perspective. Now, obviously, if you're trying to deploy a new system, always this cost performance comes into picture. You remember I mentioned in the beginning, the performance might be very good, but how much is the cost? So here, if you go into, this is a like a third party seller, they actually publicize all the list prices. Okay. So if you go to this site, colfaxdirect.com, look for vendors, look for adapters, you will exactly get the list prices. Okay. The actual prices might be different. It's just like, buying the cars. You get the list prices of the cars, then you can go to the dealers and have different kinds of deals. But then this will at least give you a rough idea of where this technology, if you want to see, okay, SDR versus FDR or Rocky V2 adapter versus Ethernet IBORP adapter, how are the pricings changing? You should be able to get a good idea by visiting this site. And similarly, Omnipath we talked about. Omnipath, after Intel, it paused for some time, and now the Cornelis network, they have introduced just at ISC, they introduced something called a Omnipath Express product. It was announced. So if you are interested, you can also take a look. And then, of course, in the convergence, it is mostly the Mellanox is selling the Rocky V1 and V2 adapters kind of things. I indicated like a Broadcom also has the Rocky V2 adapters. So sometimes in the Mellanox, because the hardware is the same, you may see a little bit of different product. For example, here, if I go into like, let's say 40 gig, that is an Ethernet standard, whereas Mellanox switch can give you actually FDR speed, 54.6 gig Ethernet. Okay. So because the hardware is the same, they can push the limit a little bit higher, which you don't see on let's say Broadcom or Arista, those kind of traditional Ethernet. So that is only the minor differences. Then in the software stack, I indicated earlier, in the beginning, it was OpenIB, that is the Department of Energy, introduced that. But once the Net Effect and Chelsea people joined, it was renamed to Open Fabrics. It actually worked very nicely for last several years. And just like, the Linux development, which happens in a public manner, Open Fabrics was working. Every 2 weeks, they have vendors discussions, and the driver was being designed. And then the Red Hat and Sushi, they were pulling from there. We were also a part of that, our Mpi library and all. But recently, there is a big conflict has started there. And that has led actually the OFED 5.3 was under development. It has stopped. This is again nothing to do with technical things. It is more political things between Intel and Mellanox. Open Fabrics versus VERFs, libfabrics. I'll just talk about all those things. So there is a new kind of a war taking place there. So in that context, Mellanox has gone its own Open Fabrics distribution. They call it MOFED, MOFED, Mellanox Open Fabrics enterprise distribution. So that is different from the Open Fabrics. So the whole idea of this Open Fabrics, as you can see, were very nicely architected. So like we have the verse interface. So if you are an adapter designer, what you can do, you design your adapter, let's say Chelsea, you design a kernel level component and a user level component. That's all you need to do. Then everything fits into the ecosystem, and that has benefits from both sides. So that means for the adapter designers, as soon as you try to satisfy the verbs, whatever the softwares are already been designed with the Open Fabrics, Ib verbs, it works. So you don't have to have like a proprietary system like a BlueZine or something design the entire stack. So then from the end user customer perspective, this also gives flexibility, because now if I want to deploy a system, I have all these choices. I can see which vendor is trying to provide at what cost and then trying to minimize. So that was a very nice ecosystem. Unfortunately, that is being slowed down. This is the Open Fabric software stack. A lot of effort was done to bring it all together. Like this is the Infiniband side, this is the iWork side. We talked about some of these IP over IP, STP. These are the various Mpi libraries, block storage access. So that was a blueprint to bring everybody together. But now what has happened, this is where the variations are happening. Some of you might have heard of this UCX stack. So that is mostly Mellanox was leading together with NVIDIA and other partners. Now NVIDIA and Mellanox have put together. So that is the UCX software stack. So the idea is that they are trying to say that, okay, everything is below, they will provide all the software stack and matching with their adapters, drivers, GPUs and all, and then the applications can sit on top of it. It's very similar to the Open Fabric stack, but this is like their integrated design. And to compete with that, Intel is on this libfabrics software stack. So there the idea is that for every NIC designer, they call it like an Open Fabrics interface. So earlier, in fact, Open Fabrics, the libIB verse was the main thing. Now it has been renamed as Open Fabrics. This is where the libfabrics comes there. So for every NIC somebody designs, they have to provide a provider. That provider should have some kind of features like the stack matching, atomics, RMA. Then you will have a through Open Fabrics interface, you can actually query and see which functionalities exist. And through that functionality, you can actually try to design your overall architecture. So now in the community, there is a big, I'll say the war is going on between libfabrics and UCX. And it is also making sometimes life hard for a lot of vendor end users, but that's how the world works. And we'll see how it'll unfold. Now to give a trend, just all these networking technology we heard about, but how they are being deployed. So here, these are some of the numbers. You can get these numbers from the top 500, but we have compiled it. So these are from the top 500. If you see, this is like a data is presented in two different manner. One is in the strictly in the count. That means out of those 500 systems, how many of them are using which network? And this is the overall performance. So that means out of those 500 systems, the cumulative performance, which network technology is contributing to what. So if you take a purely this side, you will see that the Ethernet, gigabit Ethernet, they call it, but this is not a strictly gigabit Ethernet. This combines 25, 50, 40, 100, everything has been put together. So that is a larger pie, but this is the Infiniband. And this also happened a few years back. It changed because Omnipath, if you remember, was a part of Infiniband that got split. So that is being counted separately. But if you go into the performance, so this is where you will see the Infiniband is still having a big pie, okay, because that delivers the best performance. So for almost all the high-end systems, you see the Infiniband here. It's the out of the top 500, you see 197 IB clusters. Just in the top 50, there are 33 systems. So here you will see all over the world, all these systems starting from second to up to like a 29. These are using Infiniband. Ethernet based systems here again, as you can see, this is a combination. Even Slingshot is being included there because that is the high performance Ethernet, they call it. So this the top one is the NARSC Slingshot. This is the fifth one, Saudi Aramco, and a lot of the cloud also. Like these are the AWS cloud, you can see 25 gig. And here again, there is also another kind of things are happening. Sometimes these numbers are coming, especially from China. Again, no offense to anybody. I'm just giving some technical information here. Sometimes the data centers, what they are trying to do, let's say you have a traditional data center. This may not be HPC platform or anything. They are trying to break it up. Okay, for example, if you see 147, 148, they belong to the same system. So instead of having one entry, they are dividing it and then putting two entries. Okay, because in the end, then they say that, okay, we have a more market share or more percentage. So this kind of a little bit of like a gaming is taking place in the top 500 listing. So now let's take a look at some of the performance. We'll try to give you at two levels. One is a low level and the another is an MPI level, just to give you some idea about these numbers. And these numbers are all taken from my lab. So we are providing all the details here. So for example, we talked about Rocky and Infiniband. Okay. So here you will see this is the low level, nothing to do with any upper level stack. So here you will see that they are very close. Of course, Infiniband is the best, but there is still, if you see, like around 130 nanoseconds difference or 0.13 microsecond difference here in terms of the small message latency. As the message sizes becomes larger, you don't see much difference. Bandwidth wise, you again see a little bit of difference. The Rocky is clamped with the Ethernet limit, whereas Infiniband can go a little bit higher. This is trying to show the difference between sockets, R sockets, and IB bars. Okay, so as clearly you can see, the sockets numbers are not good because it has the high overhead because it goes through the kernels. This is what we started with, that protocol processing overhead. But below, if you go like R sockets and IB bars, they are very similar. But as we discussed, R sockets doesn't have all the functionality. Like if your application only requires point-to-point, send and receive, some of these basic features, R sockets is good enough. But if you want multicast, if you want all the other Rdma functionalities, you may need to go for the IB verse. And similar things also with the unidirectional bandwidth. Here you can see like the sockets, R socket doesn't give good performance in the middle range. Of course, the regular sockets is very low. So the way I call it like a good, better, best, you can think of like this. Sockets might be good depending on your application. This is better, but this is the best. So purely from performance. Now you may need to compare that with your cost and then see where that threshold lies. And for your application, your environments, which network technology will be good. These are some numbers on the from the AWS with the EFA adapter we talked about. So there again, this is the unreliable datagram. We also talked about scalable reliable datagram. So as you can see, the SRD adds a little bit of overhead. And one thing to note, the EFA adapter performance natively is not that good compared to IB. Okay, IB, if you see earlier, we are giving like a numbers in 1 microsecond, less than 1 microsecond, where it is 15 to 16 microseconds. And similarly, the message rate is low compared to the Infiniband. But again, it is a cloud environment. Depending on your application, depending on your communication pattern, you may see that, okay, if it is not very dense communication, EFA might be good enough. Okay, so like this, you need to carry out this kind of trade-off. So then if we go into a little bit of an MPI layer, this is, I mentioned earlier, we have been working in this area for last 20 years. From the day one of Infiniband, this is the Mpi project. We had the very first MPI design with VERS in 2002 at the supercomputing. And since then, we have been continuously working. We have a lot of different versions. Currently, it is being used by more than 3,000 organizations in 89 countries. Just from our website, you will see that this is like a 1.43 million downloads have taken place. It is also available with a lot of other software stack, Red Hat, SUSE, OpenHPC Stack. We don't keep track of those. But more importantly, it also have been empowering many top 500 clusters over the last 15 to 16 years. And we work with a lot of these systems to make sure that they're able to get the best performance. So these are some of the MPI numbers. These are MHAPIS 2 MPI numbers. You can run your own favorite MPI stacks and then also see what those numbers look like. But this shows the trend. This is the small message latency. We talked about like a half of round trip. So currently it's around 1 microsecond, depending on your adapter types. So here we have listed like QDR, FDR, dual FDR, EDR, Omnipath, and SDR. Okay, these are all the contemporary ones. But large message sizes you will see is the SDR. That is the SDR 200 gigabits per second, delivers the best performance for large message sizes. And these are bandwidth, unidirectional bandwidth and bidirectional bandwidth. So in the unidirectional, you can clearly see like a bands. So this is like a QDR, this is FDR, this is the Omnipath, and EDR, dual FDR, and this is the SDR. So this is like a 25 gigabytes per second. This is being in 1000 megabytes per second here, 25 times 8. So it will be like a 200 gigabits per second. And bidirectional, it comes very close to like a 400 gigabits per second. So, and then if you take a look at the similar MPI, compare Rocky versus Infiniband, you see a same difference. Whatever you see at a lower level, it gets reflected here. Here you see around like a 0.13 microsecond or 130 nanoseconds difference between Rocky and EDR, Rocky and IB. And bandwidth wise also you see at the high end message size, you see some differences. Bidirectional, the difference is very, very small. So I hope this gives you some kind of a feeling for these numbers, and you can utilize these as a reference, because many times you see different presentations, people are presenting different numbers. So we try to include some of these numbers here. And if you go to our Mpi library site, there are a lot of performance numbers. We post every time we make a release, we actually post the corresponding numbers there. So that gives us a reference point. So if tomorrow some vendor is telling you putting you some numbers, you might be able to compare and see how good those numbers are or not. Okay. So with this, what I'll do is, we are hitting another 4 minutes to 6 o'clock. Let me fast forward a little bit, officially conclude it, and but we'll get back to this hands-on, and we'll be there for another some time until you take care of this. So to conclude here, if you remember, like we started around 3 hours back, we started with 100,000 feet level, and then gradually went down. We took a lot of history. So what we provided here
Down here
in 150 slides is like a history of 20 years. Okay, what has happened to the high performance networking? Sorry, you were asking something? No? Okay. So we highlighted the main features of IV, SC and their convergence, provided a overview of how these Rdma technologies work. We looked at some of the sample performance numbers. We also looked at the NB-Link, Slingshot, Tofu networks. Now, even though we presented a lot of this detailed history, but still a lot of innovations are happening, because as you know, the systems are heading into exascale. A lot of newer kind of workload, ML, DL, AI, which we focused in the morning tutorial, are coming. So they have different kinds of requirements. So continuously, we'll see a lot of innovations coming out in this field for the coming year. So once you have a good foundation, we hope that in future you should be able to relate to these and then try to see what these additional changes the vendors are trying to make. So with this, let me thank all our sponsors, because we have been doing this work with funding not only from federal agency, but we also get a lot of funding from different companies. All the logos you see, the hardware, we do a lot of designs, evaluations, and we bring that knowledge to you. But more importantly, these are all my heroes. What I'm trying to bring here is a work of 20 years with a lot of students, staff, postdocs, software engineers. So every time we make this presentation, we give credits to all of them. So with this, let me officially conclude here. And as I said, somewhere in the middle, we have an advanced version of this tutorial. We'll be offering that at SC because Hot Eye only does one-day tutorial. They have other presentations. So if some of you are attending SC in person or virtual, those decisions are still being made. We'll be offering this tutorial as well as the advanced version of this tutorial, as well as the DL ML tutorial, which we presented in the morning. So if any of your colleagues or you will be interested in attending those, I'll strongly encourage you. And I also mentioned like next week, we are doing this Mpi user group conference we do annually. So we'll have a 3 days event there. Hari had posted the link earlier. Search for it. We have a 3 days very packed program with a lot of keynote talks from NVIDIA, Oracle, invited talks, tutorials from AWS. Very interesting program we have put together. So if you are interested in high performance networking, it is free. It will be held virtually. So I'll encourage all of you to attend this. So with this, let me officially conclude here, and might be let's go back to the hands-on. Hari, if you can bring your slide, and we'll remain here for some more time and make sure that you take care of these hands-on exercises. So so if you are dropping off, I would like to say thank you, and I hope it was useful to you.
Thanks, Al. So whoever wants to stay on for the hands-on, can you guys like raise your hands?
Yeah, or unmute yourself. This becomes very much more easier if you unmute and then we talk directly. That becomes like a real like a classroom setting. So and I hope all of you were able to log on, and then there were no issues. Go ahead, Hari.
Okay. So please log on to the cluster. I'll give you maybe like a minute or two to log on. Please let me know if anybody is facing any issues in logging on to the cluster. So if not, we have like a set of exercises, and please note that the numbers which is seen on the screen may not be the actual numbers that you get there. These are just sample numbers that we took on a very old cluster, which is like QDR. As Dr. Panda mentioned, that's already like 10 years old. So the numbers you get now will be much better. So please execute this command. So all of these commands are available in the README file. So if you execute this command, what it will do is it will try to execute a basic Infiniband level or verbs level point-to-point latency test between two separate compute nodes. Okay. So you would see an output something like this, showing the min latency, max latency, typical latency, and a bunch of other parameters. Okay. Now, this test runs three different type of benchmarks. One is to measure the send latency, which is like a send receive semantic. If you remember, we introduced this in slides 40 through 45, the send receive semantic, the Rdma semantic. So this is going to measure the performance of all of those semantics. So it will run three different tests: IB send latency, IB write latency, and IB read latency. Okay. So you would see that the performance of the benchmark, let's say you get better latency for small messages, obviously, and you will see that latency increases with the message size. Another thing that you might notice is that the operation of the RDMA write performance is generally faster than the send receive semantic or the read semantic. Okay, so this is because of the difference in the way the basic underlying implementation has been done. So this is something that you would see. So what this tells you is that the let's say if you are implementing a middleware or a communication substrate, then it would be better if you chose the write semantic or RDMA write semantic to implement it over the send receive or the RDMA read semantic. Okay, for small messages. For large messages, the equation may be different, but for small messages, this is what we see. Okay, were all of you, or at least a few of you, able to execute this?
Is the write semantic the one where your buffers are pre-negotiated?
Sorry, can you please repeat that?
Yeah, is the which of the write or the send is a semantic where buffers between the TX and between the two hosts are pre-negotiated? That means
no, this is not the IB. This is not the RDMA, am I right? This is the
this is
this is the RDMA. Yeah, so send is not RDMA, but write and read are RDMA.
Write and read are the cases where the buffer is pre-negotiated.
Yeah, that's why you see better numbers.
Yeah, that's what I was saying. Thank you.
Okay, so I hope you guys were able to run this. So the next step will be to look at the bandwidth. So the previous experiment ran the latency benchmarks. This experiment will run the bandwidth benchmarks. Again, these are the verbs level bandwidth benchmarks that you will run. and you will see a lot of messages like this. So this kind of, again, will compare the performance of the send receive semantic versus the write semantic versus the read semantic. And you will also see that the bandwidth increases as the message size increases, and at about 4K to 8K. So a 4K or 8K is where you hit the like network MTU. So you would see that around this message range, like 4K to 16K, that is where your network gets saturated. Okay. So anything beyond that is just going to get serialized. That's what it says. And again, just as we saw earlier, you will see that the write semantic has better small message performance as opposed to the send receive semantic or the RDMA read semantic. Okay. So now let's step up one level to let's say a sample application which is built on top of Infiniband verbs. So here we are going to use the message passing interface implementation Mpa 2 as the sample middleware, which uses the Infiniband verbs underlying interface. So this script will run the OSU micro benchmarks for different kind of point-to-point operations. So it will run like latency, bandwidth, as well as bidirectional bandwidth. So latency measures half of round trip time. The sender sends to the receiver comes back to the sender, and half of that overall round trip time is reported as latency. In the OSU bandwidth, the sender sends a bunch of messages back to back to the receiver. The receiver, after getting the predefined number of messages, which is called a window, sends an acknowledgement back to the sender, and the sender again sends so many messages. So this is how the bandwidth goes. In bidirectional bandwidth, the sender and receiver will be sending window number of messages to each other, waiting for an acknowledgement and proceeding. Okay. So here again, you will see like different kind of numbers, like this will be the latency. And again, these were taken on QDR. So the numbers on EDR will be much better, closer to 1 microsecond. The bandwidth will also be much higher. And you will see that the bandwidth increases and becomes closer to line rate as the message size increases. And the latency is very, very close to what is reported by the IB verbs level. So the additional software, that is a message passing interface, adds some overhead, but it is very close to what is reported by the Infiniband verbs. Okay. So these are the hands-on exercises that we have. Were you guys able to execute these and see similar behavior? Yes, no, maybe I didn't try it out. It's too late. Let me go.
We'll need some time to try, at least on my side.
Sure.
Yeah. Sure. A quick question. Based on your experience, what type of workloads or applications are more prone to send out short size messages versus bigger messages? Just a
so if you look at it, mostly traditional high performance computing applications, like if you look at the Mpi library, which is a combination of like a lot of scientific applications, they mostly use small messages. Typical scientific applications can use all sorts of different messages depending on the problem size. Deep learning applications, especially distributed deep learning applications, use very large messages, like in the order of several hundreds of megabytes. So there was a question, are these scripts available for download? Yes, please. So on your home directory, there are all the scripts are available. You can SCP them out to your system. Feel free. So were you guys able to run it? Oh, okay. So
it is there on the slide. If you take a look at,
if you go to slide 144, you have the information on how to log in. So please go to this link, retrieve a username and password from the Excel sheet on this link, SSH into the remote cluster, and you can SCP all of these things out to your local system. So it's again slide 144. All the details are provided there. Let us know if you are facing any issues. And I hope that you have the link to the slides. So if not, I just pinged the link to the slides again. Okay. Thank you for confirming. These accounts will still be active for like an hour or so after the tutorial ends. So if you guys want to play around, feel free. Are you guys facing any issues? Are you guys still there?
Yes. So when you're comparing the IB2 and RDMA here, do you have Rocky related numbers, or it's just Infiniband?
This is a Infiniband cluster, and I showed earlier in the presentation the Rocky and Infiniband comes very close. You can extrapolate, and the Rocky will have a very little overhead on top of Infiniband.
Yeah, thank you. So Rocky and Rocky V2, will it be kind of similar? Because
Yeah,
I've seen.
yeah.
Yes.
Okay.
The performance would be very similar. Is anybody else facing any issues? Are you guys able to run this?
Yeah. Might be we can go to the next one and then.
I think no.
Oh, that's all. You had a latency. Okay. Okay. Yeah.
So if you guys don't have anything else, I think we have come to the end of the tutorial. And thank you all for attending. Hope you enjoyed the tutorial, and hope you will be able to join for a future offering of the tutorial.
Yeah. So thanks a lot. I think especially in the East Coast, I think it has been a long day. So hope, and the conference, hopefully you enjoyed the entire conference, got to connect, and have a nice weekend.
Yeah, and if you want to have any more details of what we do in our group, please follow us on Twitter. So this is our Twitter handle, Mpa. So please follow us, and you will see all of the stuff that we do in our lab. Thank you, and have a good day or night.
Yeah, thank you.
Wherever
Bye.
you are in the world. Bye.